Okay. We will be live on YouTube now, Dave. If you want, you can mute your phone, your microphone.
Okay.
Hello, good morning to everyone. We unmute everyone by default, but I would like to ask you if you can hear me, you can at least say hi. Great. Thank you, Benjamin. Thank you, Daniela. Okay, great. So we are checking that all the people involved in the first set of talks are already connected and set it up, and we will be ready to take off. So how many participants we have already? Around 40? Okay. Yes. Great. So Dave is here, and Rico, I guess, is also here. I will make both of you co-host, so you can have all the rights, Dave and Enrico. Wait, I cannot hear you, Dave.
I said I'll be able to mute Enrico when I want.
I think you this is important. You can have the control.
Right.
Okay, considering that we are almost 5 minutes to go, I will start giving the introduction of the course. So it's for me really a great pleasure and honor to host second annual workshop in advanced microscopy and biophotonics. As you may know, this is the second edition, as the title says.
Microfone não funciona no computador por algum motivo? Quando ele diz. Não precisa, não está funcionando. Ele reconhece, mas o som não funciona no Zoom. Não precisa. Oi?
I think there is someone with
Vou usar o computador mesmo.
No, there is.
Cara, o outro. Não adianta usar coisa sem fio, porque são muitas horas. Precisa ser coisa com cabo mesmo.
Okay, I don't know what happened, but I was hearing someone else. Okay, anyway, let me share my screen because I have a little flyer that I will highlight. Wait a second. Share the screen for my introduction. Okay, so as I was saying that I am very honored to introduce this second annual workshop in advanced microscopy and biophotonics. I'm very proud that we can put again this workshop on the agenda, considering all the difficulties that we are facing due to the COVID pandemic. And I'm very happy to put together this list of speakers that are all really people in the working in the state of the art of the advanced microscopy and fluorescence. We will have 21 instructors, 19 lectures and 18 application talks, 2 virtual hands-on practical sessions. One that will be done here in Montevideo and the other in California. And believe it or not, as I said before, all the difficulties that this pandemic is giving to us is also an opportunity to learn and trying to, innovate with the teaching. And we will be basically using this opportunity to share through the virtual session of all the lectures and application talks across the world. And we will be covering 11 time zones because we will start from Italy, Europe in general, and we will go up to Hawaii, where is Dave sitting very early in the morning there. And we will have, and I'm very proud that we have 62 participants from 3 continents, and here is the map with the number from the different places. So Argentina, Uruguay, Brazil, Peru, US, and Europe. So I will explain a little bit how will be the procedure for intervention of all of you. So as I said before, we mute all of you in order to control better, well, the interruption and the noise and everything. But disregard, if you want to interact, please place your question in the chat. We will take in account and basically record all the instructors, and we will also pay attention to the raise hands if you click the option in the Zoom. And after each of the activities, so we will have 3 talks, and then we will have break rooms for those of you who would like to ask and discuss in more detail with the participants. So don't be afraid to ask questions. If you have difficulties with the language, or if you are afraid or whatever, I will be more than happy to translate the question to the speakers and back to you in any time. In the Friday activities, we will have 6 breakout rooms, which will be basically related to close discussion about some topics that we pick. And all the session will be basically in parallel. So for that reason, we will have 2 rows, one at 11 and one at 10 and one at 11, and you can pick one in each of the 2. So you will have the chance to discuss with 2 of the speakers. Then I will request, well, before that, I will say that considering that we have really a high number of participants, and I'm very happy for that, unfortunately, we have to restrict the practical session because this course is intended to be as close as possible with the participant and discuss one by one and having all the sections to interact with them. And considering that now we have all these difficulties to not have the people in person, we decided to have 20 students in 2 groups, as I said before. But as I said before, the opportunity to record all the session is that we will share with all of you all the section after we finish, and you will be able to watch all the session and also have the Hangout and the software to do all the tests that we will be running, as well as the data. So I will request to all the speakers to please try to stick to the agenda. We have really tight agenda, and I will be controlling the time. So I will be giving an alarm when 5 minutes are left, and then when the time is over. And I would like to give all the information to the participant to contact me in any time. We will be checking the email and also the chat in the Zoom. So you can contact us to microscopia20@gmail.com, and as well as my email, leonardmalacrida@gmail.com. And saying that, and considering that we are at 10 exactly, I will introduce our first speaker. So Dr. David Shapson is a professor at the Department of Cell and Molecular Biology, University of Hawaii at Manoa. David is a world expert in time-resolved fluorescence with long-standing works in development and instrumentation and methods. He has a particular effort that focus on polarization and dynamic polarization and lifetime measurement. And he accumulated an enormous record of publication and several books. And I particularly emphasize one of the last one, which is Introduction of Fluorescence, which in my opinion is a masterpiece of work where he put together all the fundamentals of fluorescence. And you might think that this is an introduction and you are already an expert, you don't need this kind of book, but I will say this is my Bible, and I come back every time where I have a doubt, and there is a lot of very nice comment and alert that always help me. So I strongly recommend to have this book. Saying that, I also want to say that he is co-responsible with Enrico Graton for the Weber meeting, which is an international meeting held every 3 years, originally in Italy, then in Hawaii, and the last time in Brazil. We will hope we can have it next year or 2022. And beside all of that, of basically all his scientific achievement, Dave is really a close friend. He's a strong supporter of my career, and as well as strong supporter of Uruguayan research. And I would really like to welcome him. And today, he will be talking about an introduction of fluorescence. So Dave, you can share your screen, and you are now with the microphone on.
Okay. Thank you very much. Do you see my screen?
Yes, you just need to make a shared full screen in your PowerPoint.
Okay.
Yeah,
see
perfect.
that?
Perfect.
And with the sound. Okay, well, obviously it's a great pleasure for me to be here again. I was at the first annual workshop in Uruguay, and I really love being in Uruguay in Montevideo, and I'm sorry we're not there. On the other hand, as Lionel pointed out, doing this virtually allows us to reach people from all over the world. 11 time zones, wow. And I can tell you it's 3 a.m. in the morning in Hawaii, but it's still exciting to be here. So, at any rate, let me start off. And I realize many of you have some strong backgrounds in the field. And again, you may feel, well, I don't really need the introduction, but you never know. You might learn something new and entertaining. And I think it's important that everybody sort of starts with the fundamental information. And also, if you've come into the field from microscopy, you might not be aware of some of the spectroscopic properties. So I want to emphasize those mainly. Okay, so we start off, of course, with what is fluorescence, which seems simple, but I like to remind you that it's the light emitted by an atom or molecule after a finite duration subsequent to the absorption of electromagnetic radiation. And specifically, the emitted light comes from the transition of the excited species from the first excited electronic level to the ground level. Usually. This is not always the case, but in the vast majority of cases, that's true. And it's the development of highly sophisticated fluorescent probe chemistries, new laser and microscope approaches, and sector immunogenesis that's really led to many novel applications of fluorescence in the chemical, physical, and life sciences. And I think all of these developments will be on display in this course. So why fluorescence? Well, I always like to start by saying that it's pretty. And this is not just a glib or funny comment. I remember when I first joined the lab of Gregorio Weber, who you learn about a lot in the last lecture, in the University of Illinois as a graduate student, he explained to me that one of the things that attracted him to fluorescence was the fact that it was not only allows you to learn a lot of information at the molecular level, but it was aesthetically pleasing. And we should always enjoy the colors involved in fluorescence when we have the opportunity. Certainly, fluorescence can provide information on molecular environments. In fact, fluorescence probes have now been developed, as you'll learn, that can probe almost any chemical or physical environment, such as viscosities, polarities, pH, temperatures, et cetera, et cetera. And you'll learn about many of these probes. And what's of particular interest to me during my career is fluorescence provides information on dynamic processes on the nanosecond timescale. You can think of molecular probes essentially as molecular stopwatches. And the stopwatch starts when you absorb a photon of light and stops when you emit. And by attaching the stopwatch to molecules of interest, you can learn information about dynamic events that occur during the lifetime. So, coupled with modern fluorescent microscopy, confocal multiphoton that you'll learn about, and fluorescent proteins, such as green fluorescent proteins and others, it's providing now extremely detailed spatial information in living cells, but also information on the dynamics of the cellular components, which I think is one of the great aspects of fluorescence microscopy. And it's also very, very, very many more varies sensitive. So work with nanomolar concentrations is routine, and femtomolar, even single molecule studies are possible with some effort. Well, what are the experimental systems you can look at? Well, any biological system virtually, from protein structure and dynamics, membranes, cell organization and function, and you'll learn a lot about that in this course. Engineered surfaces for high throughput drug discovery, and live animals. What type of instrumentation is used? Well, we have fluorimeters and fluorometers, and we'll learn the difference. Of course, many types of microscopes that you'll learn a lot about in this course. High throughput plate readers and intravital imaging, and you'll learn how you can use these modern techniques to go deep into biological tissues. Now, virtually all fluorescence data required for any research project falls into one of the following categories: the fluorescence emission spectrum, the excitation spectrum, the quantum yield, the polarization or anisotropy of the emission, and the fluorescence lifetime. And in this lecture, we're going to examine all these categories, except lifetime, which will have its own lecture, and discuss some of the underlying concepts and practical considerations. And a good place to start is always the Perrin-Jablonski diagram. Some people call this the Jablonski diagram. Many of us prefer to call it the Perrin-Jablonski because Francis Perrin, you see, contributed to this before Jablonski even. But at any rate, this diagram is useful to consider sort of the life history of these excitation processes. So molecules can sit without perturbation in the ground state, and that's the S0 state shown here. And there's different vibrational levels in each of these different electronic states, and normally at room temperature, molecules would be in the ground or the lowest vibrational level. And upon absorption of light of whatever frequency it absorbs at, you can go to different excited states, different vibrational levels in those excited states, is shown here, S1 and S2. But regardless of which excited state you reach, you have very rapid internal conversion on the order of picoseconds, where all the molecules, the energy is redistributed, and you end up at the lowest vibrational level of the first electronic excited state. And there you sit until something happens to deactivate it. In our case, we hope it's fluorescence, which takes place in nanoseconds. You can also have radiationless decay that brings it down to the ground state. You, in some cases, can have intersystem crossing to go over to a triplet state, which can lead to phosphorescence. We're not going to worry about that here. And what's very important for many of the lectures in this course, you can also deactivate the excited state by passing the energy to another molecule, an acceptor, in the process of Forster resonance energy transfer, which you'll learn a lot about. So in a typical emission spectrum, the excitation wavelength is fixed and the fluorescence intensity versus wavelength is obtained. And it used to be we could only do this with cuvette studies in vitro. But now, as you'll learn, there's microscopes that allow you to get the emission spectrum also, which is very important for some of the studies you'll learn about. Here we see four different fluorophores: quinine, fluorescein, rhodamine, and bromide in their emission spectra. And I'd like to show you what these solutions actually look like under UV hand lamp. And when you've been in the field as many years as I have, and Enrico also, of course, you can look at these colors under the hand lamp and judge within a few nanometers, usually where the emission maximum is. You'll just have to trust me on that. Now, examination of a large number of emission spectra resulted in formulations of certain general rules over many years. So for a pure substance existing in solution in a unique form, the fluorescence spectrum is invariant. That is, it remains the same independent of the excitation wavelength. It's very important for many of the things we do. It also lies at longer wavelengths than the absorption. And to a good approximation, the fluorescence spectrum is a mirror image of the absorption band of least frequency or highest wavelength. And we show that in this diagram here. So this is looking at fluorescein in an alkaline solution in a cuvette, scanning the emission spectrum. And I show on the left the excitation at 280 nanometers, 375, and 470. We can see when we excite at 470, we get the largest spectrum. That's because it absorbs more at 470 than the other wavelengths. But also these raw, uncorrected spectra will depend on how much exciting light comes out of your excitation source, in this case a xenon arc lamp, the monochromator efficiency, etc. But we notice when we go to the right, if you normalize these all on the computer to the same maximum intensity, they're overlap. And this demonstrates, yes, regardless of where I excite, the fluorophore, the emission wavelength is always the same. Okay. And what about the shift? Well, here's a typical absorption and emission spectrum of fluorescein. We see the absorption in black, and we see the emission in green is shifted to higher wavelengths, lower energy. And this is called actually the Stokes shift, and we'll learn in the history lecture a bit about George Stokes, who first observed this phenomenon. And finally, maybe less important but of interest, is the here we see rhodamine absorption spectrum, the solid line, and the dotted line is the emission. And yes, to a first approximation, it's the mirror image, the emission and the absorption. And these rules follow from the Perrin-Jablonski diagram we discussed earlier. Here's an abbreviated version of it. Specifically, even though you excite to different electronic levels and different vibrational levels in these electronic levels, the emission always comes from the same lowest vibrational level of the first electronic state. So that's why the emission is independent of the excitation wavelength. And the ground state at room temperature, the vibrational levels, you're normally in the lowest vibrational level. So you're always starting from the same point, but you can go to higher levels, taking more energy, so at lower absorption wavelengths. But the fluorescence is always from the same part, and the fluorescence can go down to different vibrational levels. So if it goes to a higher vibrational level, of course, it will have a lower energy. So that accounts for the Stokes shift. And the fact that the spacings of the vibrational manifolds in the ground and first electronic state are usually similar accounts for the approximate mirror image relationship. Now, what about the excitation spectrum? Well, to do that, that's the relative efficiencies of different wavelengths of incident light to excite the fluorophore. So in a spectrophotometer, you would scan the different exciting wavelengths and keep the emission wavelength constant. And if the system is well behaved, that is, if these three general rules we outlined hold, one would expect the excitation spectrum to match the absorption spectrum. And here you see the absorption spectrum and corrected excitation spectrum for analytical naphthalene, sulfonate, and ethanol, and you see they overlap very well. I say corrected because there's a lot of instrument correction factors before you can get these excitation spectrum. We're not going to go into that in this lecture. Also, though, I want to point out, you may say, well, why do I need excitation spectrum if I've got the absorption spectrum? Well, a couple of reasons. First of all, you can get this excitation spectrum at much, much lower concentrations than you could ever get the absorption spectrum, because fluorescence is so many orders of magnitude more sensitive than absorption. But also, it's of interest, if the excitation absorption spectrum don't match, then things get really interesting. For example, consider the excitation spectrum below for a fluorophore-free in solution. Then we're going to see bound to a protein, what could happen. The emission depends on the fluorophore, of course. In this case, I'm looking at danzo, naphthalene group, and the emission would be about 470 nanometers, let's say. And this is free in solution, the excitation spectrum, which would match the absorption spectrum. But if we do the same experiment when this danzo is bound to a protein, you may see something like this. And we see that there's a big deviation down at lower wavelength, 280, for example. Well, that's because you have energy, you can have energy transfer from the protein's tryptophan residues to the bound fluorophore, resulting in an altered excitation spectrum. And also in the case of FRET, you would get alteration. So these changes in excitation spectrum can be very important for pointing out some underlying photophysics in the system. Now, the quantum yield was a concept introduced in 1924 by Sergei Vavilov, and the simplest definition is that it represents the number of photons emitted divided by the number of photons absorbed, as we see here. And notice you can't say the energy emitted over energy absorbed because of the Stokes shift. They always have different energies. So, for example, if a fluorophore absorbs 100 photons and emits 100, the quantum yield is 1 or 100%. If it absorbs 100 and emits 20, the quantum yield is 0.2 or 20%. But a more insightful definition of quantum yield would be that the quantum yield equals the rate of the emission process divided by the sums of the rates of all other deactivation processes. So here we have Kf, the rate of fluorescence, and the sum of Kd designates other rate constants that depopulate the excited state. These can be various things: photochemical, quenching, dissipation of the energy as heat, or also FRET. Now, I think it's interesting to look at quantum yields for different compounds, and here's a list from Bernard Valleur's excellent book, Molecular Fluorescence. And we can see from some like benzene, it's pretty low, and we go tryptophan, anthracene, quinine sulfate, a popular standard, up to rhodamine, which has a quantum yield of 1, so it's perfectly efficient. But I want to point out that really, whether we consider a fluorophore depends in large part on the quantum yield. What I mean by that is some molecules like adenine, guanine, adenosine, these things that make up DNA or an RNA, for example, they do fluoresce, but they fluoresce, the quantum yield is so low, 1 photon emitted over 10 or 20 or 30,000 absorbed, that they have no practical value as a fluorophore. So really, when we talk about fluorescent molecules, we're implicitly saying something that has a decent quantum yield. And I also want to point out that quantum yields are notoriously difficult to measure. And I don't care if an instrument salesman comes to your lab and say, our machine can do this really easily. That's not true. Reliable literature values for quinine sulfate, for example, from good labs have been published ranging from 0.5 to 0.7. So what I care about, if I'm reading a paper where the authors give the quantum yield, is how did you do the measurement? What was your standard, and what value did you use for the standard? Because if I think your standard should have a different value, then I can substitute. So what about polarization? I'm going to talk a bit about that, although you're not going to really discuss polarization in this course. But I think it's important that all practitioners of fluorescence be aware of the basic principles, because it's a very, very, very popular technique in the literature, polarization or anisotropy measurements. And it behooves you, it's good for you to know the basic principles. So let's start in. So we know that light can be considered oscillations of electromagnetic field characterized by electric and magnetic components, which propagate perpendicular to the direction of light propagation. Now, in these lectures, we're only going to consider the electric component. Now, in natural light, the electric vector can assume any direction of oscillation perpendicular or normal to the light propagation direction. I try to illustrate here. And polarizers are optically active devices that can isolate one direction of the electric vector. So here we see a natural light source with unpolarized light. We put a polarizer and we get one plane of polarization. One electric vector is selected. If we rotate the polarizer, we can rotate the direction of polarized light that we're looking at. Now, polarizers come in different types. In a good spectrophlorometer or fluorimeter in the lab, you usually use calcite crystal polarizers, which are very expensive, but they can go down in the deep UV, and they're among the best. Very popular to also have less expensive polarizers, these sheet polarizers, which are very good, but they're not as good when you go in the lower wavelengths. Now, of course, being in Hawaii, it's very important for me to have my own polarizers, my Maui Jim sunglasses. And many polarizers, I'm sure some of you have them, are polarizing sunglasses. Many sunglasses are polarizers. And I want to ask you, and I'm not going to tell you, but you can think about it, and can't get the answer, ask me later in discussion. What direction of polarization do sunglasses pass, the vertical direction or the perpendicular direction? So think about that. Now, consider an XYZ coordinate system where the fluorescent solution is placed at the origin. So as we see here, X and Z is in the plane of the page, and the observation is made in the Y-axis, so out towards you and the audience looking in. So you can have exciting light traveling along the X direction. You can put a polarizer and isolate one electric vector. In this case, I'm showing one parallel to the Z-axis, which corresponds to the laboratory vertical axis. Now, this exciting light will be absorbed by the fluorophores and give rise to fluorescence. And then to look at the polarization of this emission, we put a polarizer along the emission pathway and we rotate it, and we can view how much of the intensity is parallel and how much is perpendicular to the vertical laboratory axis. Polarization is simply defined as the parallel intensity minus the perpendicular over the sum of these intensities. But it's important to know about another term, anisotropy, that you see very, very often in the literature, usually designated as A or more commonly as little r, which is defined as the parallel minus perpendicular intensities over parallel plus twice the perpendicular. And we won't go into the reasons for this, but that's the definition of anisotropy. Now, let me make a comment about the difference. So you can show, given these definitions, that anisotropy is 2/3 times the reciprocal of 1 over polarization minus 1/3. Or more simply, anisotropy is 2 times P 3 minus P. For example, if you have a polarization 0.5, the anisotropy is 0.4, 0.1, 0.069, etc. And usually in modern instruments, when you're measuring polarization, it will automatically give you their anisotropy, so you don't have to calculate it. Now, clearly the information content of the polarization function and anisotropy functions are the same, and the use of one term or the other is dictated by practical considerations. And we might mention some of these as we go along. Now, when we excite an ensemble, a collection of randomly oriented fluorophores with polarized light, we're performing a photo selection process, selecting a population of excited molecules that nominally, that is more or less, have their excited dipoles lined up with the polarization direction of the excitation. This process is illustrated here. But let's look a little more closely. What actually happens when you absorb a photon of exciting light is you create a dipole moment in the fluorophore. Now, fluorophores like the one shown here, which is prodan, you'll hear about this later in the course. You can have groups that can stabilize, in this case, a carbonyl group can stabilize partial negative charge, or an amine that can stabilize a partial positive charge. And in the excited state, then, the electron cloud is dispersed to form this dipole in the molecule. And this is the transition dipole or transition moment. So when we're exciting with vertically polarized light, in this case, we excite molecules that are more or less lined up with that direction. What do I mean by more or less? Well, in fact, the probability of absorption, of course, it depends on the extinction coefficient of the molecule, et cetera, but also depends on it's proportional to the cosine squared of the angle between the exciting light and the transition dipole. Okay, so that if the exciting light is perfectly aligned with the absorption or transition dipole, the probability of absorbing is 1, cosine squared. Even at 45 degrees, you see there's a decent probability, 0.5, of absorbing. But at 90 degrees, when the absorption dipole is perpendicular to the exciting light, it will not absorb. And let's illustrate this with this little cartoon. Here we have a bunch of molecules in the ground state, and that's the direction at that instant of time what their absorption dipole, transition dipole would look like on the molecule. Now we excite with light, vertically polarized light, and we see the bright circles now correspond to the molecules whose dipoles are more or less aligned. And you see they can be a little off. The dimmer green circles are those that still absorb, but they're at a larger angle, so they don't have as high a probability. And the black circles are those molecules that the dipole was at perpendicular, so they don't absorb at all. So this is really the photo selection I'm doing. Okay, and first we're consider the case where the excited dipole is parallel to the emission dipole, okay? And let's also consider the molecule cannot rotate during the excited state. So we used to do this by putting the fluorophores in a highly viscous solvent at very low temperatures, like glycerol at minus 50 degrees centigrade. And I won't go through the math because we don't have time, but in these cases, then if the excitation emission dipoles are lined up, the highest polarization you can observe will be plus 1/2. And if they're perpendicular at 90 degrees, the polarization you would get would be minus 1/3. So the limits of polarization are plus 1/2 to minus 1/3. And that's important to know those limits. I see over the years, many students I noticed would just assume, or researchers, not just students, that the polarization, the maximum is 0.5. Well, not quite. In fact, the limiting polarization, which we call P0 in the absence of rotation, is related to the angle between absorption and emission dipoles by this expression. So this allows you to understand that limiting polarization of a fluorophore would depend on the exciting wavelength, because it depends which absorption or transition dipoles are excited, if those dipoles are lined up or if they're at a large angle. For example, this is what we call an excitation polarization spectrum for tryptophan or indole, virtually the same. And we see the dotted line as the absorption spectrum, and the solid line with the points are the actual measured polarizations. This is for indole and glycerol at very low temperatures. And we see it's very complex because of multiple overlapping absorption paths. This measurement was actually done by Bernard Verlour in Gregory Weber's laboratory many years ago. Now, let's look at another molecule, rhodamine, B, embedded in a lucite matrix. So this is a room temperature, but it's in a plastic matrix. It can't move. And again, we see this variation of polarization depending on the wavelength. We see at wavelengths above 470 nanometers, you get up to nearly to 0.5, the theoretical limits, but then you can get some very low polarizations below minus 0.2, for example, when that absorption dipole is at a large angle relative to the emission. Here's GFP. I'm sure many of you probably never seen this. I did this in my lab where you normally excite, of course, in the visible where you have a high polarization, not 0.5, only about 0.42 or something, but you can go lower. So why is it important to know these excitation polarization spectra? Well, so you can choose the best excitation wavelength, of course. So if we go back to tryptophan, maybe you're studying a protein. And many people studying proteins like to excite the protein with 295 nanometers because tyrosine no longer absorbs at that wavelength. And they say, well, then I can look at the tryptophan in isolation. That's fine, unless you're doing polarization. As you can see, then you're going to be near the minimum value. So if you're doing polarization studies on a protein, it's better to excite near 300 nanometers. And this has become particularly important in the last couple of decades when many people use laser sources. And obviously the lasers will have different and fixed excitations. For example, if you use the helium-cadmium laser, one wavelength that it emits at is 325. If you happen to do that in GFP, you would get a low polarization. Of course, with an argon ion laser at 488, no problem. But that's why it's nice to keep that in your mind, what these values are. In the case of multiphoton excitation, the limits are different because you're getting essentially a selection process on top of a selection on top of a selection, as shown here. So in the case of one photons, the limiting polarization is 0.5 or anisotropy 0.4, which is 2/5. We see the R0 is 2/5. For two photons, R0 is 4/7. For three photons, you can even get up to 2/3, 0.67. So you have some advantage for doing polarization with three photons, or multiphotons, I should say. Now let's consider what happens when the fluorophore can rotate during the excited state lifetime, because the fact is many of you probably aren't interested in only looking at samples in glycerol at minus 60 degrees centigrade. Well, we might have the absorption dipole, and the emission dipole may already be at a slight angle. But during the excited state lifetime, we can have rotation of the molecules, so the emission dipole can change. And in fact, you get additional depolarization occurs if the dipole can rotate through an angle omega. And then the observed polarization, P, is related to the limiting polarization. Of course, that's always your starting point at the wavelength you're using, times 2/3 cosine squared omega minus 1. So you observe the polarization, and knowing the P0, you can see what angle it went through. For example, if we have a distribution in solution, we excite with polarized light, we do our photo selection. Now we can have Brownian rotations of the molecule during the lifetime of the excited state. And Francis Perrin related this already in 1926. We rewrite his original equation in terms of polarization measured, P0. Lifetime, of course, the lifetime is important. The longer the lifetime, the more time it has to rotate before emission, and the birotational relaxation time rho, which is the time for a given angle to rotate, a given orientation of a molecule to rotate through an angle given by the arc cosine of 1/e, 68.42 degrees. Now, if we have a spherical molecule, ρ0 would be equal to 3 eta, which is the viscosity, V molar volume over gas constant temperature, For a spherical protein, it follows then you would have 3A to M, the molecular weight, times the partial specific volume and the degree of hydration. And that's fine for what you would expect for a protein. And of course, if you have ellipsoids or other shapes, it will be different. And that was studied in detail by Gregorio Weber, as we'll mention later. But it's also important for us to know that eta is the viscosity. So yes, the more viscous the surroundings are, the slower the rotation. And that's relevant for membrane studies, as we'll see later. So if a fluorophore is free in solution, it could have a fast rotation, which would give a low polarization. It's bound to a protein, for example, or macromolecule. It could have a slow rotation because of the slow tumbling of the protein and a high polarization. I want to also point out that in the literature, you'll often see a term rotational correlation time donated as T sub C instead of the birotation relaxation time. And correlation times originated in the NMR field, and it's the time for a dipole to rotate through 55 degrees, the magic angle in NMR. And the information content, though, is similar since rho is exactly 3 times tau c. So it takes 3 times as long to go through 68.42 degrees as it does to go through 55 degrees. But it's important when you read the literature, you have to be clear if people are reporting rotational relaxation times or correlation times, because it really changes. Now, consider the case of molecules associated with proteins, for example. Like if you have non-covalently associated, like porphyrins, FAD, NADH, ANS, we'll give other examples later. If the probe is bound with any appreciable free energy of binding, it has to be held to the protein matrix by several points of attachment. So its local mobility, that is, its ability to rotate independent of the overall global motion of the protein, is very restricted. But if it's covalently attached, we'll talk about those reactions soon through an amine group or sulfhydryl group, or in the case of tryptophan or tyrosine side chains, you can have considerable local motion of the fluorophore, plus you can have domain movements. And I show this here. In this case, the protein I'd worked on, tau 7, tau 12, it's a dimer. We have overall rotation of the dimer. We can have movement of one domain, a C-terminal domain relative to other domains. And we can have movement of a di-molecule around the point of attachment. All of these will be polarized. Now, what do we use polarizations for? Well, it's very good for looking at different things. For example, aggregation state of a protein. Let's consider a protein dimer monomer equilibrium. So we have a dimer, we have a fluorophore on it, and as we dilute it, it can dissociate. Okay, so you can either follow the intrinsic protein fluorescence sometimes or put on a suitable probe and follow this. Now, when I say suitable probe, in the case of polarization, what we really mean are probes of a suitable lifetime. That's why it's important to know the lifetime of the probe you're using for these measurements. For example, if we have a probe of a very, very short lifetime, less than a nanosecond, you're not going to get any sensible rotation of the dimer or monomer. You'll see very, very little change. If you happen to have a probe of a ridiculously long lifetime, hundreds of nanoseconds, which is possible, you might have complete depolarization during the excited state lifetime. So you have to choose the right lifetime. Here we see the rotation of, we show the monomer is faster than the dimer, so the polarization would be lower for the dimer to the monomer relative to the monomer. And again, I note that the lifetime is very critical for these measurements. So you can simply make a plot of polarization or anisotropy versus concentration to look at the dissociation. Here we see fluorescein FITC labeled lysozyme, which is a monomer at all concentrations we look at. And so nothing changes. Here we see the protein now 7, now 12 that I sort of illustrated before. And as we dilute it from micromolar to nanomolar concentrations, we see a drop in the polarization, which is due to dissociation. Okay, now it's the change in polarization that matters to us. And for a true dimer monomer, I should go over almost 3 orders of magnitude, specifically 729-fold in concentration, to go from 10% dimer or 10% monomer to 90%. And I don't care why I get a particular polarization. Why is the polarization of the monomer about 0.15? Well, it has to do with all the local rotations involved. But that's not important, you see, when we're looking at these sorts of measurements. The same when we use it to study protein-ligand interactions. Here's a case of a fluorescent GTP, well, a non-hydrolyzable GTP gamma S binding to dynamina GTP binding protein. Before we add the protein, the anisotropy or polarization is very low because the mat probe is free in solution. When we add the protein, it goes up and up and up, and I can get a nice binding isotherm. Basically, I can get the binding constant, about 8 micromolar in this case, when we take into account the change in the quantum unit upon binding. So these are very easy and quick methods in cuvettes to do these binding measurements. And it's interesting to note that this approach revolutionized clinical chemistry when Abbott Laboratories introduced the TDX machine in 1981. This is fluorescence polarization immunoassays. And this was important because up until this time, immunoassays were done using radioactivities. And finally, there was recognition that this is dangerous and people wanted to get away from that. And that's where Abbott Labs came up with this machine. And the idea is to add a target, a fluorescent analog of the target, a drug, a barbiturate, a metabolite, whatever, and you have an antibody to that target, and you measure the polarization. First, you have the fluorophore bound to the target, the antibody, then you add biological fluid, blood, urine, etc., and you're looking to see if there's the target in there, and it will decrease the polarization by displacing it. This is just shown here simply. So you have an antibody to the fluorophore labeled antigen, get a high polarization, you add the unlabeled antigen, and it displaces it by mass action, and the polarization drops. So it's very easy, and you don't have to, in radioisotope work, you'd have to isolate pure, free, and bound. You don't even have to do that. This method is introduced by Danliker originally. And I want to show a diagram from the original Abbott Lab paper, first author Mike Jolie, who I knew pretty well. And we see they're showing polarization versus concentrations of gentamicin. So they used a fluorescently labeled antibiotic. What's of interest is look at the units there. And I highlight this. This was in the first paper. For convenience, they represent the units as millipolarization, where 1 MP, 1 millipolarization unit, is 0.001 P. Well, I went up there in 1981 in Chicago, where they were located, and said, why on earth do you do this? Why don't you just use the polarization? And they explained to me, well, they wanted this to be a point of care instrument, so in doctors' offices, et cetera. And they showed this to a number of doctors, and they said, well, it looks okay, but you're going from like 0.2 to 0.1. This change is so very, very small. It's not very good. So they changed it to millipolarization. Now you're going from 200 to 100. And the doctors all loved that. They said, now we have a change. So, of course, I pointed out you should have called it nanopolarization. You have a really big change. But this is why in clinical chemistry, you will almost always see these millipolarization units, and they call them milliPs or millianisotropy units. But this is very common in clinical chemistry. And you have high throughput polarization plate readers now. And even there, as you see on the screen, they're displaying millipolarization units. You can even do fluorescent polarization microscopy. I don't think we're talking in this course about that. And there are some technical issues because of numerical aperture effects. We won't go into that, but some people have done this. Here we see an anisotropy image where they're looking at different circumstances at the polarization or anisotropy of a GPI anchored proteins in cell membranes, but it's not so common. So let's move to another topic, Forster resonance energy transfer. It's named that after Theodore Forster, who made some important contributions to this. And what is FRET? Well, we have a donor molecule, we'll call it donor. There's nothing else happening. It absorbs light and emits light like any fluorophore. But if you have an acceptor molecule, which has the right characteristic nearby, we'll define what we mean by that soon, you can have transfer of excited state energy, radiationless transfer from the donor to acceptor, and the acceptor fluoresces. If the acceptor is a fluorophore, you can have a dark acceptor. You don't need to have a fluorescent acceptor. Now, I like to give this tuning fork analogy, which I learned from Anton Visser, a longtime fluorescence friend of ours. And if you have a tuning fork, we used to do this when I was in elementary school, and you hit it with a rubber mallet, it starts vibrating. Now you have another tuning fork nearby, which has the same characteristics. When that energy from that vibrating tuning fork reaches it, through the air in this case, it will start vibrating too. It has the right frequency. And this is sort of what's happening with energy transfer. You get oscillations of the electric vector in the donor, and if you have a match with the acceptor, you can get that oscillating, and then the emission can come from that. And we talk about the Forster critical transfer distance, which is the distance R0 where you get 50% energy transfer between donor and acceptor. So how far away must the acceptor be to see energy transfer? And that's going to depend on the refractive index, the quantum unit of the donor, kappa squared, the orientation factor, which is the most difficult one, which is the relative orientation of the donor of the dipoles of the donor and acceptor, and the overlap integral. You have to have some overlap between the emission spectrum of the donor and the absorption spectrum of the acceptor. And you can determine these efficiencies by looking at the decrease in donor fluorescence, for example, by intensity, or you can do it by looking at the lifetime. Then you would have the efficiency from the change in the lifetime of the donor in the absence and presence of the acceptor. And as you learn in this course, lifetime determinations are much more robust than intensity measurements, and you're going to learn in following lectures how FRET and lifetime data are handled, largely in the microscope. What about fluorescent probes? We might ask, where do fluorophores come from? Well, some occur in nature naturally, like quinine. We're going to talk a lot about that in the history lecture. And there's many natural fluorophores, like aromatic amino acids of proteins are intrinsic fluorophores. Modern fluorescence studies would not be possible without fluorescent molecules designed and synthesized in the lab. In fact, the rapid development of biological fluorescence owes as much to synthetic organic chemistry as it does to modern molecular biology and commercialization of instrumentation. And most beginning fluorescence practitioners today don't have to synthesize their own fluorophores, since thousands are literally available now. But even as late as the 1970s, when I was a graduate student with Gregorio Weber at the University of Illinois, only a handful of fluorescent probes were commercially available. Consequently, for some of my studies, I had to synthesize the probe, build the instrument, and walk 5 miles uphill to the lab every day, through the snow every day to the lab. Okay, maybe I didn't have to walk 5 miles through the snow uphill, but the rest is true. So let's talk about probes. We talk about in vitro probes used in cuvettes or in silico plate readers, or in vivo probes, more accurately in cells. We can classify them as intrinsic fluorophores. These are fluorophores that are naturally part of the system, or extrinsic fluorophores, fluorophores we have to introduce into the system. Here's some pictures of intrinsically fluorescent molecules. You'll learn a lot in this course about NADH, and FAD is very common to porphyrins. If you take the metal out or take the iron out, you can have fluorescence from porphyrins, and there's other ones. And proteins, of course, have naturally occurring fluorophores, namely the aromatic amino acids, phenylalanine, tyrosine, tryptophan. As we see from the lower left, the absorption of tryptophan is much stronger than tyrosine and phenylalanine. Okay, and on the right, we see the emission of the tryptophan is well separated from tyrosine and phenylalanine. And that's why, and the fact that there's fewer tryptophans than tyrosines and phenylalanines usually, why people like to use tryptophan to study proteins, and especially they like to have single tryptophan protein. Now, extrinsic fluorophores, these again, as I said, are dyes you add to the specimen to introduce fluorescence. You can have non-covalent interactions that'll bind just thermodynamically bind reversibly to a specific region, like an antigen-antibody interaction, or covalent interactions, where you can react covalently with a specific functional group. So extrinsic probes, for example, some probes that bind to proteins are these famous aniline naphthalene sulfonates, ANS, we'll talk about that later, SANS, TNS. And when they bind to hydrophobic patches on proteins, the fluorescence is enhanced, as we'll see. You can have probes that bind to DNA. Probably you all know ethylene bromide and DAPI, different Hawks dyes bind to DNA. What about covalent attachments? Well, the first covalent fluorescence probe utilized was actually anthracene isocyanate, made by Albert Kunz in 1941 for labeling antibodies. But he was looking at serum, blood serum, for example, and interference from autofluorescence led him to prepare fluorescein isocyanate. Now, Riggs and colleagues in 1958 described fluorescein isothiocyanate. You see the sulfur group replacing the oxygen, because it was easier to synthesize and it had much more stability than isocyanate. So FITC since then has become probably the most utilized probe in history. Gregorio Weber, who we'll learn more about later, in 1952 synthesized danzo chloride to attach to proteins to study protein hydrodynamics, and this initiated the field of quantitative biological fluorescence that we are in today. But it's interesting to note that one of the big increases in interest in fluorescence was due to the company started by Richard and Rosaria Haugland in their kitchen in Minnesota in 1975. Molecular probes. Many of you have heard of this. And for a brief time, they were located in Plano, Texas. And their first popular product was Texas Red, we see here, which was the sulfonyl chloride to covalently attach to proteins like antibodies. It's the big thing, immunoglobulins, to label antibodies. And that was a very popular, made them a lot of money. In the early 1980s, they moved to Oregon. And in 2003, they were bought by Invitrogen for $325 million. I understand 200 million went in their pockets. So it is true, you can become rich in fluorescence. Enrico and I haven't quite found this pathway yet, but it is possible for young people to aspire to. And an interesting series of probes they made, which has become very important, is the Alexa Fluor series. In 1999, they published this paper describing these probes, saying that there was a need for probes with high quantum yields and high photostability. That was because people were really starting to do microscopy. And fluorescein, which was a common probe, would bleach so readily. It was so non-photostable that they needed other probes. By the way, they named them Alexa after their son, Alex Haugland. That's why they're called the Alexa probes. So they designed a series of probes where, based on other fluorophores, coumarins, fluoresceins, rhodamines, but by making the right substituents, they introduce a lot of photostability. And here's an example which they published. If you look at Alexa Fluor 488, which absorbs emits like fluorescein, you can see it's much more stable than fluorescein is. Now, I should say there are new probes. We'll mention some later on. Certainly Addo dyes, daylight, and other probes, Janelia probes, that are even more stable than Alexa probes. So this has always been one of the goals of developing probes for microscopy, to have photostability. And here we see the Alexa fluor dyes that go over quite a wide range of wavelengths. So you can get, this is for amine labeled things. What about labeling? Well, proteins have reactive groups like lysine residues or N-terminus NH2 amines or cysteines. And then you can put the reactive groups on your probe depending on what you want to label. And the fluorophore will depend on the light source, the spectral properties you want, maybe autofluorescence you're overweighting, etc. And of course, when you label, you want to be sure to test that it doesn't alter the biological activity. Now, Gregorio Weber and colleagues introduced polarization to study physical state of lipids and monomembranes, an idea he had in his PhD thesis. Actually, they used perylin and other non-polar fluorescent dyes. And years later, Mayer Shininski, who was a postdoc with Weber and a co-author on that paper with Barinholtz, introduced DPH, diphenyl-hexatride. And for many decades, this became the most popular membrane probe. In recent years, as you'll learn a lot in this course, Loredan has become one of the most popular fluorescent membrane probes. This was introduced by Fay Ferris and Gregorio Weber. Fay was Weber's technician, I think in 1979. And you'll learn a lot about Loredan in this course, so I won't go into that. But it's interesting to look at, I did a search on PubMed, and we see the DPH fluorescence papers go up and up and up from starting when it first 74 in the early 90s, and then it starts slowly going down. And it's interesting because Loredan started going up in the 90s. It was introduced, really used by Enrico and his collaborators in the 80s. But as the Loredan started to go up and up, the DPH starts to go down, and I think that's cause and effect. Well, there's obviously fluorophores for a wide range of ions. You can get for sodium, calcium, magnesium, anything you want, and anions. And very, very popular probes for fluorescent probes for calcium determination. I should say virtually all of them use the same theme of the 4 carboxylic acid groups, which is like an EDTA, which chelate the calcium. What about fluorescent proteins? That'll be the final part of, almost the final part of my talk. Well, as our friend Richard Day and his collaborator Davidson said in this book they edited, it's certainly been a fluorescent protein revolution. And I think you all know why, because you can take the gene for your protein of interest and attach to it, using molecular biology, the DNA of the gene for a fluorescent protein like GFP. Then when it's expressed, you have your target protein linked to a fluorescent protein. And the first one in this series was green fluorescent protein, isolated from the Aquaria Victoria jellyfish by Shimomura. And he was actually interested in the aquarin bioluminescent compound in the jellyfish, which absorbs, which gets excited by some movement and emits blue light, which is absorbed by the GFP, which is nearby in the jellyfish. The GFP then emits the green light. Why would you want to do this? Well, because as you know, the sky is blue, right? That's because blue is scattered much more readily than the green light. So green light will go farther. And why do they do it at all? I heard a nice explanation from a marine biologist. You don't do it to scare off the prey. The jellyfish and other things that do this do it because when they're attacked by a prey, they give off a flash of green light in the hopes of attracting a bigger prey fish to feed on the predator that's after it. So it's an alert system. Now there's been people like Roger Sen in particular and others show that you can mutate amino acids around the chromophore in the GFP and get many different colors, and there's a whole rainbow of coloring now. And I got some nice slides from Richard Day from a fluorescent course he taught. You get now, besides from the jellyfish, you get them from corals. The DS red was one of the first ones. Here we have a nice turquoise. Here's a ruby from a coral. Here's an orange. And even from fish, here's neon green from a certain fish. And here's a nice PowerPoint from his lecture, which he credits to Adam et al., where you look at the brightness of different fluorescent proteins as a function of the emission wavelength, normalized to EGFP, the hydrogen atom of the fluorescent protein. We can see there are some much brighter and some weaker over a wide range. And you might consider this when you're choosing fluorescent proteins for your studies. How many are there? Well, hundreds. I asked Richard J. He says, who knows, hundreds and hundreds. And he gave me this nice paper where you can look at the evolution of the green protein and how, or fluorescent protein, some species lost it early on and some kept it right to the end. And humans lost it later than some others, but we did lose it. And I like to think that it's unfortunate. Think of the possibilities of fluorescent protein genes were not lost early in human evolution. But that's another story. There's other techniques like biomolecular fluorescent complementation, and Tom Kerpel has showed you can actually split the fluorescent protein into two halves and put one half on one target protein, one on the other. And if they come together, you might get fluorescence. Not always, but if you do, then you know they were together. There's other tags like halo tags, where you attach a dehalogenase to the target protein, and then you can add solution any fluorophore you want linked to the alkane that reacts, links it to the target. Similar but different chemistries are used for snap tags and clip tags. More recently, we have a series of Janelia probes made by Luke Lavis and Howard Hughes, and he developed probes that are much brighter and much more photostable, and these are becoming very popular. And I like these fluorogen-based probes by Gautier, and these papers describing these are in your PDFs, I believe. And he attached sort of a little antibody type molecule to whatever probe he wants, attach that to the protein of interest, then the fluorogen doesn't light up until it binds to that. Finally, we have quantum dots. In the 70s, Alexei Akimov first made these, and they're semiconductors. So inorganics, usually cadmium selenide or other ones. And he observed that when you get different sizes, you get different colors. So we can see on the right the different emission spectrum of different size quantum dots. And the quantum dots have been functionalized, so you can now attach them to many different molecules. And they're very, very bright, very photostable, but of course they're very large. So they're not useful for every application, but they're still becoming more and more popular in fluorescence. So any rate, at that I'm done, and I see I've been an hour and 1 minute, so I'm on schedule. So I'll stop sharing and turn it back to you, Lionel.
Hey, Dave, excellent timing. Excellent talk as usual. So now we have some time for questions. If there are any questions in the audience, please raise your hand or write in the chat, or then you will have the chance to still discuss with Dave during the break rooms. Meanwhile, well, Ernesto Ambrogio has, can you unmute him? Okay. Ernesto, I think now you are active.
Okay, can you hear me?
Yes, hi, Ernesto.
Hi, Dave. Thanks a lot for your talk. Really nice.
Thank you.
I have a question. You know, these photo-switchable fluorescent proteins like EMIOS2, or I can't remember all the names, but I wanted to know whether you can make a point on these guys about, you know, polarization, quantum yield, when you photo switch, for example, from one wavelength to another?
Wow, that's an excellent question. And I can say, I don't know. I would guess that they're useful because when you get, once you're in the switch to the bright fluorescent state, I'm assuming the quantum yield and certainly the polarization is going to be the same, because all of these chromophores and these fluorescent proteins, as you know, are made from 3 amino acids fused together in the protein interior. Okay, and these are very rigid, so they're not moving. So the polarization properties are the same. What could be a little different in the GFPs, of course, is the lifetime changes. And I didn't go into that, but most of these fluorescent proteins have slightly different lifetimes, which will affect the polarization you're going to observe. But in terms of quantum mute, I don't expect much difference, but I actually don't know. And Lord knows before I ever give this lecture again, I'm going to look that up. So I'll be able to answer the next time.
Okay, great. Thanks so much.
Sure.
Okay, excellent. I am looking at the chat. There is no more questions. And so I think we can continue, Dave. Thank you very much for the talk. We will have you tomorrow, as well as the, well, wait, there is one more question here. Well, wait a second. We will ask this question. How to deal with the fact that many fluorophores could interfere with the structure and function of protein of interest?
Well, that's why I made, yes, that's a good point. And this is often used by people that say, oh, you can't use fluorescence. Well, in fact, you can. But of course, when I was labeling, whenever I have an enzyme and I'm labeling the protein, of course, you check the activity. And if it inactivates the enzyme, you usually can't use it for fluorescence studies. On the other hand, it's telling you something about some functional group near the active site. But it's common, for example, in the O days, if I was ever worried, you can put an excess of substrate into the system and label the protein when that's bound to the active site. That's a common technique. But certainly it's something to be aware of. Now, it's interesting because I will note that I used to hear the criticism all the time from the biologists when I'm trying to publish studies with a protein labeled with the fluorophore. Yet once the biologists started to use green fluorescent protein attached to their protein of interest, and green fluorescent protein is very, very, very big compared to a small fluorophore, they don't seem to criticize that. And in fact, you should be aware, and it's happened to me in a couple of cases with my collaborators, where we can demonstrate that the green fluorescent protein could affect the biological function. When we studied dynamin, we actually measured the activity of green fluorescent protein labeled dynamin, and it was completely as active as regular dynamin. But yes, it's something you have to be aware of, but I wouldn't panic about it. You can test the activity if you have it, and hopefully it's still active, and that's the best you can do.
Okay, great, Dave. Thank you very much. There is another question from Sebastian Acuña about the Jablonski diagram. But if you don't mind, I will answer this question during my next talk.
Sure.
So you can go. So thank you, Dave. Thank you very much.
Okay, so, I will mute myself now.
Yeah, great. So the next talk is given by me. So let me just share the screen. Okay. So it's weird that I have to introduce myself, but I just want to say something which is important for the course because I didn't say before. So I am a professor at the Department of Pathophysiology, the Clinical Hospital, the School of Medicine, Universidad de la República. And I have a shared position between the Universidad de la República and the Instituto Pasteur as the head of the Advanced Bioimaging Unit. And basically, all my motivation is due to the instrumentation, some methods related to spectroscopy on images. So I will talk now basically about some details of instrumentation related to fluorescence. So, well, as you know, I mean, the opportunity that brings the fluorescent microscopy is unique because we can go from a few millimeters to tens of nanometers, covering a whole range of different techniques, from diffractive limit microscopy to super resolve microscopy. And fluorescence is really a powerful tool in order to find the particular object that we want to find within our system of study, like, well, viruses, bacteria, cell, animals, etc. So we know that basically we have to handle with the problem of the resolution, which is due to basically the optics we use, as well as the wavelength. And at the end, no matter what, we will have a resolution which is limited in the axial and the lateral, depending on these two variables, well, the numerical aperture of the objective that we use, as well as the wavelength. And if we use probably a visible range wavelength, our resolution, no matter what, will be on the range of 200, 300 nanometer in lateral and 500 to a micron in the axial. So, but the good things about fluorescence is that basically we can use different approaches, like wide field fluorescence, in which we focus the light within within the optics. Unfortunately, these have a lot of out of focus fluorescence, and this is how it look like, for example, when we do wide field fluorescence. In comparison, confocal microscope will reject the out of focus, and we will see how in a minute. And this is important because we can cover different region in the cell with zeta stack resolution. This is also done by another technique, which is called a spinning disk, which is kind of a similar approach of the laser scanning confocal microscope, but with lower resolution. But as usual, the limitation in one side are advantages in another. And for example, in this case, you can go really fast scanning multi-points and basically have a resolution of the rate of the camera. The other possibility is, for example, TIRF, which is an effect that you can excite fluorophore near to the surface, and these are very useful when you are studying things in the membrane. So the most novel techniques related to super resolution that can be split in three. I will not speak much in detail because we will have a very nice lecture, couple of lectures on the Thursday by Luca Danzano and Fernando Stefani, are related to, well, the true super resolution, functional super resolution, or stochastics. Basically doing different kind of approximation, we can break the diffraction limit, and today we can go up to nanometers, as we will see in these lectures. So, but what we need for doing a fluorescent microscopy? Well, of course, we need a source of light. So in our case, for confocal raster imaging, we will use lasers. We will need to move the beam. So we will need to use a scanner or some other strategies like piezo stage. I will address all of the options, and then we will need to detect the light. So for this, we will have two main groups, I will call, basically one related to point and the other related to many points in parallel. So the PMTs, APDs, or the cameras. And then I will cover some other stuff about little things about optics and electronics that we need to do this kind of approximation. So when we compare wide field microscopy versus confocal microscopy, basically for the wide field, we use a source of light that can be an halogen or a mercury arc lamp, and we shine the light, and we have here a dichroic mirror that can reflect the light, and then a filter who select the wavelength that we want to use to excite our sample. And in the way back, this dichroic mirror enable the pass of the fluorescent light, which is usually larger, longer wavelength than the excitation. Then we will have another set of filters that we collect the band that we want to collect, and then we will have different configuration, our ISPs or cameras, different kind of camera with different path. You may notice that here we will collect all the light coming from, up and down of the focal point that we are interested in. So to avoid this, the confocal microscopy use an object in the optical path, which is called the pinhole. And the pinhole rejects any point which is out of the focus what we wanted to see. This is really a great advantage, and basically changing the pinhole, we can change the resolution, but of course, if we close too much the pinhole, we will restrict a lot of light, and we will be unable to see anything from the sample. Considering that we have the pinhole, of course, we will be acquiring a point, which is called the point spread function. So we need to basically move our beam, and for instance, we need basically a scanner. So basically, during the imaging technique, we use a laser scanning microscope, and this can be used in regular confocal microscope, super resolution microscope, as well as multiphoton microscope. And here I place some examples. Basically, the scanner are a set of two mirrors who are moving orthogonally to each other, and they have different configuration depending on the kind of the scanner, and I will cover in a minute. So here are different brands from my confocal microscope. For example, here is an Olympus. This is a FloorView 1000. These are the one that we have here is the size 880, and there are many others. And this is an ALVA microscope for STED that they have at the Laboratory for Fluorescence Dynamics. This is a nice instrument for do super resolution. So for the scanner speaking, well, we have basically two sets that I will discuss. One is related to scanning a single beam or scanning a multi-beam. So for the scanning a single beam, as I said before, we have two mirrors which are moving independently. One will move the beam horizontal and the other will move the beam vertical. And this will allow us to basically do the raster scanner across the image. So the good or the advantage of this method is related to the good quality of the images and the high resolution that we can get. And one of the disadvantages is the slow frame rate that we can get, which is on the order of 3 frames per second. This depends on the kind of scanner, and I will discuss about raster scanner versus resonance scanner, which enable to go faster rate. The other possibility is to use a multi-beam, and for this, it was designed, the spinning disc confocal microscope based on the Nippon's disc, which has basically a micro lens and multiple pinholes, and we can collect light coming from different places in the sample at the same time, and then acquire all of them in the camera. This is going very, very fast because we can read many of these pinholes during the time that we are acquiring 1 frame rate. And the thing is, one of the advantages that we have are the video rate that we have. And the bad thing is the low resolution that we have during the acquisition, because we cannot have exactly the same size of the pinhole. And this is related with that the pinhole is fixed in the size. The two kind of configuration during the raster scanning confocal microscope are, for example, the scan mode, in which we shine our light as usual with the dichromatic mirror to select excitation through the emission, and then we have the couple of the mirror from the scanner, our scanning optics, the light goes to the sample, get excited, our fluorescent came back, and pass through all the scanner back to the detectors. In that case, it's called the scan because the beam after passing back from the scanner is stable and is not moving. And this is basically how is most of the time set all the confocal microscope that we have in our laboratories. One of the disadvantages of this is as much optical path we have, of course, we will lose light in each of the surfaces. And this is something that we need basically to handle with. So the other possibility is to use non-scan configuration. And this is possible, for example, in the multiple photon excitation, because as we will see in a minute, 2-photon excitation is intrinsically confocal. For instance, what we can do is use the scanner. We still pass through our scan optics, and then we can split the light from the excitation and emission before coming back to the scanner, and our beam will be no longer stable because it's not canceled by the two mirrors. So basically the beam here is moving, and what we need to do is use optics right in front of the detector to focus as much as we can the light on the active area of the detector. This is very good when you want to save surfaces, because we can put our detector right after the light coming out from the sample. And this is, I know, a couple of instruments with this configuration that work pretty good. Well, we say that we need to use light, and for confocal microscope, we use different kind of lasers, such as the helium neon, argon laser, diode lasers, and more recently, diode pump solid state laser, which are very stable and very cheap in comparison with the previous one. But all of these lasers are continuous wave, which means that we have more or less an intensity, a constant intensity over the time. And these are not able to use for measuring fluorescent lifetime, because we need pulse laser or modulated laser that we can do for different approaches, like using acousto-optic modulator, some other alternative, pocket cell, etc. But I will not go in detail on this characteristic. For this film application, we can use supercontinuous lasers, which are, for example, the white laser that they have at the LFD, the Fayanion, and also this other from YSL. They are very stable. They cover a long range from UV to couple of microns. They are really powerful, and they are intrinsical pulse at different frequency. For example, this one is a 20 megahertz frequency. Moreover, we can have also multiphoton excitation, and in the market there are different options. The good thing about multiphoton excitation is that we move our excitation to the near infrared, and this is very useful, as I will explain in the next slide. And they are really powerful. And basically, we have several brands. The new ones from Coherent are the Chameleon Vision 1 and 2. Spectra Physics have several different options. The one that I pick here is the MiTi Deep C with the Deep C model, which is a model to correct dispersion of the pulse passing through the optics. And in this model, EHP is the one with a short pulse, which is very useful for increase the excitation. This is the one that we got here to build the diver, and I will address this at the end of the talk. Then Tolab came up with this Tiberius, which is the most cheap of the others. It covered a short range from 710 to 980, but for most of the application, it's a very nice instrument. And there are different companies. This is from Kalmar. The Carmel 780 is the one that we got for the other microscope that we are building. Is a 2-photon inverted microscope, and this is a femtosecond fiber-based laser, which is very nice. It has only one single wavelength, but is really 1/3, 1/4 of the value of the large 2-photon excitation, 2-photon laser, sorry. Then there are some others, 2-photon laser based in different crystals that can cover a longer range. For example, these two can go from 690 up to 1250, 1300, or more or less in the two. I have the chance to use this inside in the LFD. It's a wonderful, very stable laser with a lot of power, and it's really fast switching the wavelength. It's a nice instrument. What I want to address here is what is special in 2-photon excitation? Well, if you go the easy thing, which is go to Wikipedia and ask what is 2-photon excitation, the definition says that 2-photon excitation coefficient is based on the idea that the absorption of 2-photon of the half of the energy need for 1-photon excitation can also excite a fluorophore in a quantum event. The process, the 2-photon excitation process, depends on the quadratic function of the light intensity. And for instance, we will call these nonlinear processes. this struggled my thought about how this happened over the years. And until I put time, I never understood why this happened. And well, as Dave explained before, we have excitation in the Jablonski-Perrin diagram, and then we have some electronic rearrangement before the emission. Well, if we talk in time, the excitation is usually on the femtosecond time scale. Then we have relaxation on the picosecond time scale, and the emission takes on the order of nanosecond time scale. When you thought about this, you notice that if you don't have two photons within this period of time, basically to hit the first intermediate state and the second before the first one will release the energy, this will never happen. And this basically give me the final hit to finally understand this. Well, if you really want to put two photon excitation, you need to do something, because if you wait for the probability to have two photons, this will take forever. So basically, Maria Goppenmeyer described all the mathematics about this. And basically, what is important here is, well, on the contrary of the continuous lasers, two photon lasers are pulse, as I said before. And the width of the pulse is usually on the 100th of femtosecond. And this is basically very important, because we need a lot of power concentrated in a pulse, concentrating in terms of time, and then focus with our optics to the point. And if we achieve all of this and we apply the power enough, we will get two photon excitation on the spot and none above below of this point. So this means that two photon excitation is intrinsically confocal. And what is special about two photon excitation? Well, the first thing is basically we have an increased penetration, because in the range that we use for two photon excitation, there are is the minimum of the absorber that we have in tissue and in our samples, our classical sample, biological sample, but also is also a window where the scattering coefficient is low, relatively slow. So as increasing the wavelength, the scattering is inverse to the power of 4 of the wavelength, and this is important to basically penetrate deep in the tissue. The other important thing is the avoidance of autofocus. And here are basically the excitation with a regular wide field, and this is the two photon. And you may see that there is no excitation up and down of the point, which basically is important not only for the confocality, but as well to avoid photobleaching above and below or the point where we want to image. So if we come back to the scanner, well, as I said before, we have a raster scanner, which are fast and simple. Well, we have two ways to scan the beam, sorry. We can scan the beam with the scanner, where the sample is stationary, and there are different kind of scanner. The galvanometric is the most common. The resonant are not that common, are a little bit more expensive, but they are faster. The difference between these both is that in the resonant, we have the mirror moving back and forth with a certain frequency and not stopping, and this allows you to go faster. As usual, one and the other have different advantages and disadvantages. The galvanometric are very precise, resonant are not, sometimes are not, the new ones are much better. Then we have also polygon scanner, which is like this one, and we have also the use of acousto-optic deflector that can move the beam across the sample. So this is the one that we have here in the two instruments that we are now building, the diver microscope that Enrico will talk tomorrow, and a regular inverted epifluorescent detection two-photon microscope. This is very nice scanner from Cambridge Technology, which has 10mm mirror, which is a very nice room to accommodate your beam already spanned, so you don't need to deal with the scanning optic to fill up the back aperture of the objective, which is very useful. And it has a 40 degrees excursion angle. And as I said before, it's really fast and it's very linear. In the market, there are different sizes of the scanner. The most common are the 7-8 millimeter. And in the diver in California, for example, they have the 15 millimeter, which are very, very large to accommodate larger beams. The other possibility is to scan moving the sample, and this can be done using piezo stages, in which we can have really, really good precision in the movement, nanometer resolution, and we can move across the sample X, Y, and Z. The only constraint is, of course, it will take more time. So next move on to the detectors. And considering the detector, I will speak first about the point detectors. And we can split basically between two main groups, the photomultiplier tubes and the photodiode detectors. The first one can be found with different coverage, like bialkali, multi-alkali are the old ones and the more common in all the confocal microscope. And the new one are the gallium arsenide phosphodiene, which you may see are better in the resolution. One of the important things is usually all these detectors have really large areas which make much more easy to basically focus the light in the detection zone. On average, all these PMTs are on the 30% of the quantum efficiency, and this is a comparison between the different surfaces. They have different response in the spectra as well as in the sensitivity. And you can see here that the gallium arsenide, which is the red one, is the higher, and you can go up to 50, 70, even a little bit more quantum efficiency, which are very useful for most of the photon counting detection that we do using film. Then we have the avalanche photodiode that can cover also a long range as the PMTs, depending on the material that we place in the active detector. And the most important thing is the quantum efficiency of those are very, very high, much better than the PMTs. And you can see this in the response that we have at, for example, 600 or 650. The problem is, of course, you have, depending on the surfaces, different ranges. And if you compare, for example, this APD with the gallium arsenide phosphodiene, which is this one, you may see that the range is much larger for the gallium arsenide phosphodiene. So how photomultiplier applies work? Well, we have a cathode and an anode, and then we have a series of diodes, and basically this is under the backbone, and we basically, when a photon hit these surfaces, it will produce photoelectrons, and after the photoelectron will hit the successive diode, it will amplify the release of new photoelectrons. Usually the multiplication is on the range of 4 to 5, but can go up to 18. And after all the step, which usually are 8, you can amplify really quite a lot the signal coming from a single photon. These are most of the configuration that we have, and depending on the kind of instrumentation that we can do, we can have this side-on photomultiplier, head-on. There are different variants. They are useful depending on the kind of spectroscopy that we can do. While they are extremely sensitive, they can be really, really fast on the gigahertz rate. They have a fast response, which means the time to take from the photon, the active surface at the end to the anode. And this is the common thing, as I said before. The other thing is the avalanche photodiode. And in that case, the physics is a little different. We have a semiconductor based on silicon. They can dope with different molecules and metals, and this can give you different response in spectra. But basically, we have a positively doped region and a negative doped region, and then in the middle we have a neutral charge depletion region in which we can apply this reverse bias, which is the potential, in order to increase the number of secondary photoelectron produced after the first one hit to the surface. And I found very interesting this animation in the web page that you can play around with the number of photons hitting the surface as well as the reverse bias. And you can see that if I increase from 1 to 10 the reverse bias, this increases the number of photons that you can, the amplification that you can find. Well, as much as you increase this reverse bias volt, of course you start to increase the dark current. And this is, well, the bad side of this. I didn't say, but PMTs are very good in the signal to noise ratio. More recently, there are some new kind of hybrid detector in which they combine the two technology, first amplification and then the APDs, and this increased quite a lot the sensitivity, taking the best of each of the technique. And this increased a lot the quantum efficiency, and you can read really fast. These are ideal for lifetime measurement as well for FCS because it doesn't have after pulsing, which is a problem when you want to do correlation experiment. So then we move to the parallel detector, and I split in two areas, two sets of detector. Basically, the classical cameras that we will see in a minute, the CCDs, the intensified CCDs, the electron multiply CCDs, and the scientific CMOS. But these are the most common used for basically all the wide field, spinning disks, total internal reflection, light sheet microscopy, and many more. The main difference with all of them, I split basically this intensify because you can use this for film measurement. The other set of cameras I call nano cameras because these are actually PMTs or single photon avalanche photodiode arrays, which can be run as a nano camera. And you will see in some of the lecture that we can use, for example, the ID detector to see correlation within the different actuators. And this will be a talk by Lorenzo Scipioni tomorrow afternoon, I think, yes. And then he will talk also about the new microscope he is building, about 32 channel for spectral, which can be also used as a nano camera. And there are a bunch of people working in the field using this SPD array, for example, in the Vigilomiti lab at the Italian Institute of Technology. They're using this for fluorescent lifetime imaging on a 25 array sensor, which is very nice. Well, speaking about the difference between CCD and CMOS, well, these two, the main difference is how the data is read, and also how is the sensitivity and how is the size of the chip. Well, in the CCD, each of the actuator, which are usually diodes, can be excited, and basically we have a shutter which is total. So we will not be able to acquire a new image until we read all the data. And the data is coming out one by one to the amplifier and the charge to voltage conversion. And until we get out the last pixel, we will not be able to take a new measurement. And this is the main difference between the CCD and the CMOS technology, in which we have here a rolling shutter. Each of the actuators are up independently. All of them have their own amplification and conversion. And basically, you read all of them line by line, one after another. And this makes a huge difference in the speed that you can read the two. And this is see here in the table that you can go, for example, in a regular CCD to 17 frames per second, and with a any of the scientific CMON, you can go up to 100 frames per second without any problem. Well, in terms of noise, these two are kind of similar. Usually CMOS are more noisier, and the noise in this case is all the noise is different because all the pixels are different. In here, basically the noise is very stable along the all pixels that we have in the camera. But nowadays, there is in the market new cameras, for example, this one from Photometrics, which is back illuminated, and you can go up to 95% of quantum efficiency, which is really, really a good competitor for the EMCCD's camera for single molecule. And you can see here the difference between the two resolution and the signal to noise in these two cameras. So in the electron multiplying, they have electronic that amplify basically the output of the signal, and this enlarge basically the signal to noise, which can reduce the noise basically to less than 1 electron in this. And you can see the difference between the three, the CCD, the CMOS, and the EMCCD. The cons of this is, well, usually the pixels here are larger, and you still have the time that you can read, because no matter what, you have to wait until the last pixel can read to get the new measurement. So then we have some other parts which are very important for the microscope, and these are electronics. For handle with the data, for example, for lifetime measurement, we use Flimbox, and these two technologies, Flimbox this is based on Spartan 3 and Spartan 6. These are ISS Flimbox that can handle with the lifetime measurement. And this is the new technology based on the Kintex, which is Spartan 6 car. And these are very nice car that you can make parallel measurement, and Lorenzo Scipione will talk about this in his presentation on Wednesday about the spectral film instrument that he has built. And also we need basically some optic to split excitation and emission, and I will speak in a minute about this. To read the scanner, to move the scanner, we also need cards. And usually, well, most of the microscopes come with this 3-axis card in which we can handle with the position of the scanner and move the scanner to rust scan. We use here the IoTech card, which is a very cheap solution, and you can do it by your own. And this is the way that we solve how to handle with the drivers of the scanner and connect with the microscope and make the microscope work. Speaking about the signal, so the signal coming from the detectors, as I said before, we can use basically steady state measurement, and the IoTech card is also useful in that sense. There are different options, like for example, FCS card from ISS, and there are so many others in the market. And as I said before, film card are used for frequency domain measurement, and Becker and Hickel also have some other for time domain, which are based on the time to correlate the single photon counting procedure. And the new ones are these 32-channel FPGA developed by Film Lab in Italy, based on the work of Alessandro Rosetta. But if we are talking about analog detector, we need to condition the signal in order to have a photon counting regime. And for this, we need amplify the signal, and we need to include quantum fraction discriminator, which are need to transfer the data from analog to digital and then get into our car. And this is basically the sequence of the electronical step that we need to use for the microscope. So finally, I will just make a mention about the optical filters that we use. Basically, we usually use dichromatic mirror, which enable to basically split signal depending on the wavelength. They can be short pass, long pass, or band pass. And then we use usually band pass filter that can be based on two technologies, interference filters, that are deposit of different layers of material that can interfere and enable or not the pass of the light, or colored glass filter which absorb and reduce the transmission for certain wavelength. So finally, I would like to comment the instrumentation that we have here at the Uruguay, and in particular to the Institut Pasteur, and as well as the Hospital de Clínicas, where I am located. Well, in Uruguay, we have several confocal microscopes. For example, in the School of Medicine, they have the SP5. This is a spectral microscope with several lines and excitation. It has a resonance scanner and a galvo scanner. This enabled to work with CO2, temperature, and many other adds that they include over the time. They also have fluorescent capabilities. The Instituto de Investigaciones Biológicas Clemente Estable, they do have 2 confocal microscopes, and all upright, still working confocal microscope from Olympus, and also the new one, LSM 800 from SAI with the ID detection, which is a very nice instrument to do sort of super resolution that we can reduce to the half of the regular confocal microscope. And also it has the cabin for CO2 and temperature, and they do have also an epifluorescent microscope. At the School of Engineering, we will have on Thursday, basically a participant from the School of Engineering. When they are building new microscope, basically one which is called an epifluorescent microscope with a multifocus epifluorescent based on electrical lens. So the sample is not moving, and they are moving basically the focus where are looking with the electrical lens, and we will see how this works in some other talks. And they are now working on SPIM with adaptive optics for work with cells in a large view. Here at the Institut Pasteur, we have 2 confocal microscopes, one 800 and one 880, which is a pseudo-spectral detection, because we can collect the spectral detection step by step along the range that we set up. And then we also have an epifluorescent detector for simple measurements. So the 2 projects that I am working on now are, one is, as I said before, an inverted microscope based on this Carmel 780 Faber-based 2-photon laser, and then it will be built on top of this Nikon TI-S microscope. We got basically motorized stage, the scanner that I speak before, detector that I talked before, and the ISS fast film in order to do film measurement, also phosphorescent lifetime measurement, FCS, 3D orbital tracking, and most of the technique that we will cover during the course. Then we are working on in another 2-photon microscope. This is the famous diver microscope that Enrico will introduce on Wednesday. And this is a unique microscope for deep tissue imaging, harmonic generation, and autofluorescence. It's based on a large PMT in the trans detection. And we will see how this works. It's very nice. It has a really large scanning optic that enables to have large field of view, and these are very useful for in vivo or for large tissue samples. And we will use this beautiful 2-photon laser, which is the MyTI, as I said before, with the deep sea model and the EHP model with a shorter pulse, which enable to increase up to 3-4 times the excitation efficiency in depth without increasing the power laser. And this is also important when you work with the in vivo samples. We will use the same scanner as the other, and we will be using this new 4-channel film box based on the development of Alessandro Zeta from Film Labs in Italy, which are really nice card that you can go up to gigahertz of frequencies. So with this, I would like to thank Hontao Chen because I use most of the slide for his talk at the Laboratory for Forensic Dynamics, as well the supporter that helped to do the research, but also to organize this event, as for example, this funding from the cooperation or between Uruguay and Mexico government, which are very important for things that we are doing in order to work together in South America. So thank you very much to all of you. I think I am very good on time, so we will have enough time for questions. So I'm gonna stop now my sharing and see if there is anyone raising hand, or if we can keep going to the next speaker. We are more or less in time. So if there is no question, I would like to just pass a message within all of you, and this is related to how to organize the breakout rooms after Enrico talk. As I said before, we will split those of you who would like to chat with the speaker in 3 rooms. If you don't want, you don't need to go. And basically, the idea is if you can place in the chat just the number between the 3 talks, we will always have 3 talk and break. So we will label the first talk as 1, 2, and 3. And this means for us that we will place you in the break room with the speaker. And if you don't want to go to any break room, we will basically keep on the Zoom, and you can stay until we come back. In this time, we will have a long break because it's lunchtime here, but you can also go out and then come back after before we recombine at 1:30. So if there is no question, I think I will introduce our next speaker, Dr. Enrico Graton. He is professor and the biomedical engineering department in the University of California, Irvine. Since 1986, he is the PI of the Laboratory for Forensic Dynamics, and Enrico is a pioneer basically in everything that we will cover in this workshop. He is in his long-standing career, he developed most of the technique that we will see and we use every day, and I can name basically all related to correlation, like 2-photon FCS, first measurement, line scan, circular scan, RIGS, NMB, part correlation, PCOM, the connectivity maps, the 3-orbital tracking, and of course the phasors. So he's author of hundreds of papers. The microscopy is not only the main area of his develop, the biophotonics is another big area, and he is just the recipe of the Britain Chance Award, which is a big achievement for given by the SPI Society. He is also author of dozens of patents, and he is the former mentor of more than 80 postdoc and PhD and more. For me, it's really a great honor that we can have him today, and I can have his support to bring this beautiful workshop that I have the chance to attend every year since I moved to the LFD as a postdoc. And he's always really a person that inspires and provide motivation to any of us. So I really want to thank Enrico and give you the word for your presentation. wait, Enrico, we are not hearing you. Can you unmute, Marcela? Enrico, wait a second. We are not hearing you.
Okay, now?
Now, yes. Perfect.
Okay, so I will try to share again my screen.
Yeah, perfect.
Okay, so can you see my screen now?
Yes, you have to
My
share.
voice. Okay,
Yeah.
well, thank you very much for the introduction, Lionel. And of course, everybody knows that Lionel has been in my lab for some time, and we have a lot of fun and also a lot of publication together. So for the question, I speak Castellano, so you can ask the question in Spanish or any other language. I don't speak Chinese, but anyway, so just don't feel obliged to speak in English with me. Okay. So as Lionel says, I've been working on many different subjects. I am not so young anymore, so clearly the age contributes to that. And in California, where I am now, the sun is coming up, and I think in Uruguay now is lunchtime. So I will talk today about FCS, but from the point of view of single molecule. This is my interest, and I start with this slide, which I always show at the beginning of my talk, in which you can see a cell, and the cell might be, you have a dark side, which is the nucleus, because the protein that we are looking doesn't penetrate in the nucleus very much, but the protein aggregates in so-called focal addition. This is bacillin EGFP, so aggregate in focal addition. And the question I have is the following. So focal addition forms in terms of might be minutes, and involves about 100 or more different molecules, and you have many in the cell. In order for the cell to move a focal addition in the leading part of the cell, so the part that is moving in this direction, will have to disassemble and reassemble again. And all these processes continuously happening, and this is something which happens very frequently in any biological process. And this is a case in which the focal addition are all different, and might be the association of the proteins are different in the particular focal addition. So you can have a system in which is highly reproducible. So the cells to move needs a focal addition, but there is no stoichiometry, specific stoichiometry of how to, in this assembly, which is different from many other processes. But the question is, how a molecule, which is, for example, in a leading edge, can in part go into the nucleus or in part go in the other side of the cell. So what is the path that the molecule will follow? And you can see from the very beginning, I put the accent on the word molecule, and I want to see if it's possible to follow a molecule. And then in the cell here, you can have 1 million of molecules, but you want to observe one in particular going from one position to another. And there is no super resolution of anything that will be able to give you a single molecule, but we will use this method, which is based on fluctuation spectroscopy, in which we can follow single molecules as they go through the cell. Okay, so first of all, let us start some introduction. And so molecules in the cell can move in particles, which are moved by motors, but a motion, which is always universal, is the diffusion of molecules. And diffusion of molecules is a process that took some time to understand, and not necessarily we understand completely, and not in a cell, because in a cell, there are different kinds of diffusion and motion that we have to take into account. But there are some general rules about diffusion, which I represent here by this graph. I hope you can see my mouse. So what is happening is that if you have, for example, all the molecule in a given position, so that indicate the position at a given time, as the time evolves, the distribution of this molecule remain Gaussian according to a fixed second law. And since this is a probability, as the curve of the distribution broadens, you can see that the integral have to remain constant because it's a probability. There are many kinds of diffusion. For example, Dave talked about a rotational diffusion, which depends on various factors. But the main problem is diffusion. And diffusion is a universal way of molecules to move. Maybe it's not important for cells or not important for animals. We don't diffuse, or at least we pretend not to diffuse. But what is happening is I want to study this mechanism in cells, and in particular in the interior of cells. So where is the name, and who was one of the first people studying Brownian motion? And this Brownian comes from Robert Brown, which was an English botanist, which about now more than 200 years ago was studying the motion of particles, which are pollen grains. And the idea at that time that was that every form of life, including plants, he was a botanist, start with some sort of seed or some sort of molecules or structure that gives rise to life. And then he says, well, in the animals are sperms or other forms of aggregates, but in the plant they have to be the pollen. And then in order to show that pollen is origin of life, he said, well, if it moves, everything that moves because it's alive. And so he observed under the microscope by eye, because we didn't have any of the beautiful detectors that were described by Lionel, the motion of the pollen. And pollen is small enough, and he was observing the motion. So he went to he was part of the Royal Academy, and he went to give a talk about the origin of life and the pollen as the origin of life. That doesn't, because it was moving. He said it moves, so it has to be alive. And apparently there is a record of his talk, and in the record of his talk, somebody asked, but how do you know? Have you done anything which is inanimate and for sure doesn't move? It's not supposed to move. And he said, of course, if it moves, it has to be animate. Well, in coming back to his lab, he ordered to his assistant to look at the motion of things which are inanimate. And he took a piece of wood, making little pieces and putting them in the microscope. Actually, the assistant did that, and the little piece of wood were moving. And then that was a surprise, and for Robert Brown. And Robert Brown said, well, might be because they're alive. And then there is a record that he ordered very, very old wood from the pyramids in Egypt, which were 6,000 years old, and they say they have to be dead, and they were moving. And so everything that he has observed was moving. And so that today is known as the Brownian motion, which is affecting every object. And the explanation of the Brownian motion comes from Albert Einstein. Actually, Albert Einstein never did an experiment, but he was able to give an explanation about this motion. And he knew, of course, theories of gases, and he used the explanation why molecules in gases move, but applied to a liquid, to a solid. And here I have a drawing that I will use later on. So in blue, little blue are essentially molecules of water, is a schematic diagram. And in red are particles, which can be protein or can be anything else. And he says, well, there is a continuous exchange of motion and energy between the particles that move and the molecule of the solid. And that motion and that exchange of energy and momentum is what makes the particle move. And then he was very, very convincing in this proof, which was based on theory of gas. And then people start to consider that not necessarily only living things will move, but also molecules will move as well. And that was known from the theory of gas. But let us see this drawing and what that means and what Einstein also observed. So we can see that a motion which is similar to diffusion, for example, could occur if we have a particle that moves in a potential. And simply the activation, so going to the next potential well and so on, will occur because you give some energy, and that energy is given by the Boltzmann distribution. But you can see that I can draw as well, if I use this picture, a very deep well. And once a molecule gets in a very deep well, will take much longer time to get out of the deeper well and perform what I will call apparent diffusion. And this is shown in this diagram, in which a molecule maybe will stay in a well for some time, and then once in a while will start in another and go in another well. So that means that actually the motion not always occur because of all the wells are the same or all the jumps are the same, but in a system which is complicated as it can be a cell, it's possible to have a trapping in one particular position, maybe a binding site, and then going to a different position and so on, but still is under the form of the exchange of energy with the medium, with the system. Okay, so let's go back to fluctuation spectroscopy, and let us see who are the important people in this field. So as I said, about 200 years ago, was introduced the concept of Brownian motion, and Einstein gave an explanation about 100 years later. But at that time, there was a lot of interest in understanding noise. And there was noise in resistor, which is called Johnson noise. Nyquist was a very important contribution to that. And all the mathematics of noise was developed around 1920, something like that, on the idea that all objects, including telegraph line and telephone lines, are subject to noise. And people study that noise very careful, and they discover actually that no matter what they do, the noise was always present, and it was always present because it was coming essentially from the cosmos, from the origin of the universe. And they discover in that way the origin of the universe just by studying the noise. So there were many other people who were interested in. So let's go more modern. And I have the name of Manfred Eigen, because Manfred Eigen was interested in the noise in chemical reaction, but from the point of view of single molecules. So how a chemical reaction occurs, and why some reaction goes faster and goes slower, and so on. But it was really by the work of Elliot Elson in 1972 that he did the first FCS, which F stands for fluorescence correlation spectroscopy. Today, we used to have for fluctuation correlation spectroscopy because other objects can also, not necessarily is related to fluorescence. And so Elliot Elson wrote a famous paper in 1972. He's the first author with Doug Marte and Ward Webb, and it's in a physics journal, and in which he described the reaction of ethidium bromide with the DNA. So it's a chemical reaction, and he studied the time it takes for ethidium bromide to bind and to unbind, and doing so, studied the part which is chemical reaction. And I have a picture of one of my students, which is Keith Berland. He's now a professor in Emory. And he was one of the first, actually, the first application of two-photon FCS in cells. And we have to wait a lot of time to have a commercial instrument that people can use in order to measure fluctuation. So there is another very important part of measuring diffusion, and I have the name of Dan Axelrod and the picture of Dan Axelrod. and the other method, which is based on perturbation, and it's called a FRAP. FRAP stands for fluorescence recovery after photobleaching. So you have a system of molecules. You can, by zapping with a laser, very high power, to destroy, for example, the fluorescence of the molecule. But due to the transport of molecule into that volume, you will recover part. Actually, part can be also not recoverable and so on. But in this experiment, which is very nice and has a lot of success and a lot of people use, you don't care about a single molecule, although the process is due to the single molecule. But fluctuation spectroscopy cares about the single molecule, but cares in a different way, and cares in the following way. So suppose we look at the same system, and I dilute it a little bit, so I have less molecule, and then we observe a molecule. You observe a given volume. So for example, in this volume, I have 1 to 3 molecules, and then after some time, I can have 2, and so on. And what is happening is that the average intensity will fluctuate if I measure a single point, and will fluctuate with the given rules, which are given by the way I observe the volume and by the transport, that the equation of transport that will bring the molecules in that volume. And now you can see that here I put the accent on single molecule and not here, which can very well be a concentration of molecules. Okay, so let us talk about this number fluctuation, because this is crucial to understand FCS in general. So the number fluctuation says that the basic idea is that any open volume, so a volume which is connected to a reservoir where it's very large compared to the volume I'm observing, the number of molecules or particles fluctuate according to a Poisson statistics. Of course, if the particles are not interacting. So in a given volume, I can observe 3, 5, 1, 2, 4, whatever, a sequence. So if I'm able to observe a single volume, I can observe molecules going in and out of that volume. And since the distribution, the spectral distribution, due to chemical physics reason, is Poissonian, the average number will depend on the concentration of the particle. So the Poisson distribution is a distribution in which the variance is equal to the number of particles in the volume. But this principle, which is the occupation number, doesn't tell anything about the time a fluctuation will stay there. And so let's go to the next step. So in comparing FRAP, in which we have a system at equilibrium, which is indicated by this line, the system can be out of equilibrium, positive or negative, doesn't matter, and then recover to equilibrium with a given law. In FCS, also, we observe a system at equilibrium, which is that line, and which is exactly the same value, the average value. But the fluctuations occur, positive or negative, and that fluctuation occurs because simply molecules can go in and out the observation volume. And while here we have effects which are synchronized in time, here we have all the effects which are not synchronized in time. And this is very important because we have to find in mathematics a way in which we can see all those fluctuations, put them together and compare with the fluctuation that we expect if we can synchronize it. Of course, in a system which is spontaneous fluctuation, by being spontaneous, there is no way we will know when the spontaneous fluctuation will increase, will be high or low, and so on. So we need a special mathematics. And that mathematics was developed around 1930, 1940 to explain noise in general. Okay, so this is a famous experiment done by Svedberg, and I copied this table, which is in the first page of the paper, and this observation was done by what Svedberg called ultramicroscope. Today we will call a spin microscope, in which a sheet of light was illuminating a solution which contains gold particle, and he was looking with the eyes and dictating the number of particles he can see every second. Actually, it has a metronome that was scanning the second. So, and he was saying, I see 2, 1, 2, 0, 0, so no particle, 2 particle, 0, 0, 1, 3, 2, and so on, and so on. And then he stopped. He stopped because he was silent to count the particle and dictating, and then he started over again. And that was a clearly great observation, because if this is a total random sequence, you can stop and start all over again. And you can see all the points where that stopped. And that is important because the fluctuation in this case, you see 1, 2, 0, 0, were counting the particles, in that case, gigantic particles, gold nanoparticle, that he was observing in the microscope. But that gives you an idea that the fluctuation is given by particles, or molecules, as we call. Now, this is the same graph in this page that I draw again using Excel or using any software. And now, if you look at this part, at this graph, which is the same sequence I have there, which is, I will say, it's the raw data, but it's irrepeatable because it's random data, I observe something which is, there is no word in Svelberg paper, that there is something strange about this sequence. So you see more or less the average value can be between 2 and 3. But then once in a while you get a fluctuation which is much larger, and once in a while you get nothing. And if the system will fluctuate randomly, why, how come that for a long period of time I never see 0 particle, and so on. So if you actually look more in detail, you will see that there is like a fluctuation in the number of particles, and here and here and here, and so on. So this intensity that I draw here from the data of Svelberg didn't pay any attention to that. Otherwise, my BFCS would have been discovered very, very earlier, much earlier. But it contains all the information I want to do. And actually, this is a very simple experiment for those of you who are interested in teaching, that can be for teaching fluctuation in a system. And of course, you know, you have the average number, and he plot the Poisson distribution. So how many times I observe a given number of particles, 0, 1, 2, 3, 4, 5. And he demonstrated that actually the occupation number follows the Poisson distribution. Fine. But he didn't observe that the relaxation time, so that in order to change the number of particles, he has to calculate something different, something which is related to essentially the average of this curve, which we learn to do, and that is called a correlation function. Okay, so let's go back to the observation of single molecules. So what can cause the fluctuation in the fluorescence signal? Well, clearly the number of molecules in the fluorescence volume, as I say, and that will change due to diffusion or binding if the particles get correlated and they don't move, or they move altogether. Then, of course, for example, conformational dynamics, you have seen that the spectrum of the protein can change very much depending on the conformation of the protein itself. So conformation can be the origin of fluctuation. A rotational motion, if polarized reviews is either in excitation or emission, can also give fluctuation. And then finally, I have protein folding, blinking, which becomes very, very important today for super resolution, and many other things that can be directly observed in FCS. Okay, so let us focus on one particular thing, which is, let us suppose that we have a volume of observation, which is very important, how that volume of observation can be obtained. We have molecules which are going in a Brownian motion, a random motion, and once in a while, a molecule will cross the volume of observation. Well, when it crosses the volume of observation, will produce a signal that we will observe. Notice that the signal can be scattering, can be anything, doesn't need to be fluorescence, but it generates a signal. And then we will see the changes in intensity measured by a microscope in that particular volume. So the important thing here is the volume. How, of course, the smaller is the volume, the larger will be the fluctuation. And most of the time, if the volume is very small, no molecules or no molecule that we want to measure will occupy that volume. So till comes the 1 photon and 2 photon. I will not spend any time here, but just to explain that in 1 photon, we can have a confocal volume, which was the first one used by Manfred Eigen and Rudolf Rigler in order to describe this process. But today we can do in another way, which is using 2-photon excitation, in which case you have seen that the emission of fluorescence can come from a very small point. So I will not go through that because we already did that. But I want to stop in this part and to point out why it took so long from Svedberg, or let us say from 200 years ago, Brownian, Robert Brown, to observe those fluctuations. So suppose we have a millimeter volume, which is a cuvette, and my standard is 1 micromolar solution of most molecule, small molecule that will be important in water. So in a millimeter cuvette, which is a millimeter, so 1 millimeter by 1 millimeter order of size, okay, well, this is 10 millimeter actually, is we have on the order, if we have 1 micromolar, we have on the order of 10 to the 14 molecule, 6 times 10 to the 14 molecule, which is a very large number. So it will be very, 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 very difficult to see any fluctuation. But the other important thing is that the time it takes a molecule to cross a volume of the order of 10 millimeter is on the order of 10 to the 4th second. So if you want to mix something in a cuvette, shake it, because otherwise it will take forever due to the fusion. Okay, let's go immediately to a picoliter, which is a typical cell. So now we have, instead of the size of a typical cell is, let us say, 10 micron. Of course, it's not a cube, but it's 10 micron. And now we have in that volume much less molecule. So something that might be we can start to measure. But the important thing is that it will take a much shorter time to cross that volume. So that shorter time can only be measured if you have a detector. The eye will not be sensitive to that. And then if we have in a confocal volume like we will deal, so it's about 1 micron by 1 micron by 1 micron, we have on the order, even at 1 micromolar, we have on the order of 100 molecules, or 600 molecules. But the time it will take to cross that volume is a fraction of a millisecond. And that is really a very small amount of time, and we need very sensitive and fast detector in order to measure. So we need 2 technologies. One, how to create a volume which is small. And second, how to measure a fluctuation which is very fast. And that took some time, and only in the end of the previous century, we were able to have technology that was able to measure that. Okay, so how the signal appears, and let us see what are the characteristics, because this is really the important thing. So this is the same experiment that was done by Svedberg, but we did now at much higher frequency. So the time is in microsecond, it didn't have a microsecond. And then when a particle will cross the volume, we will see a certain number of count, and so on. And first of all, we can expand, so we can zoom in one of those events, and we can see that there is a duration. And what is the duration? So the duration, the average duration will be the average time a molecule occupies the volume of observation. And then there is a distribution of, in this case, of photon counts. And you see sometimes I will have maybe 100, sometimes I will have 600 or 700 or whatever, 600. And you see that there is a distribution of amplitude. And that distribution of amplitude today we call the photon counting histogram. So it's essentially the histogram of the values you see here, which give us information, so about what? About the time it takes the molecules to give to pass through the volume, but will give also about the number n of the molecules that we have, and also about the time it will take, so the distribution of time. So the distribution of time is measured by the correlation function. So, but there are two quantities, and I will not discuss today the amplitude of the fluctuation, but I will discuss only the duration of the fluctuation. The amplitude of the fluctuation goes under, under the name of photon counting histogram, or also NMB in the case of cell, and it will be discussed in other lectures. Okay, but let us talk about the duration. So we have fluctuation, that was the average, and those are the fluctuation. And we need to know how long a fluctuation which is high will go to low, or which is low to go to high. And we build this quantity, which is called the correlation function. The correlation function depends on the how far an event in time we measure or we correlate, and we take the fluctuation of the respect to the average value of the fluorescence. We multiply by the value of the fluorescence at a given distance, so that if that is negative and that is positive, will be the same if that is positive and that is negative. And then we normalize, this is a very important thing, to the average value. So we divide by the average value to the square. And that is a quantity. If you see, you have an F here, an F here, an F to the square here. So it's independent on the unit that we use to measure fluorescence, and is called the correlation function. The correlation function, so a time when the time is very zero, is called the G0, the G at time 0, which is essentially the variance divided the average, which will be equal to 1 for the Poisson distribution. Or otherwise, at very long time, will always go to 0, because the fluctuation which occurs in this point, if we look at the very far point, will be uncorrelated. Okay, so now we need to express the fluorescence in terms of some general model. And let us see what is happening here. So we say that the fluorescence is given by the product of observation parameter, how good is the filter, how much you illuminate, and the quantum yield. Of course, if the quantum yield is 0, there is no fluorescence. Then we have another part, which is a part which is given by how the volume is excited and how the concentration of molecule or the number of molecules change in that volume. And of course, now you can see that that part is essentially a common factor. This is the illumination volume. So everything depends on the illumination volume and where the molecules are in the illumination volume. So that is very important, and that is one of the problems with FCS that we will discuss later on. Okay. So what is the excitation volume? So in this plane, okay, what we call the XY plane, so the light is coming in this direction. The illumination volume is always Gaussian, or approximated by Gaussian. Of course, it will be the Airy function. And it's actually not written as a Gaussian, but it's written as, because in a true Gaussian, that will be 2 here. And then we have a quantity we call the waste of the illumination volume. And then the Z, which is different if we have essentially confocal system, we have a 2-photon system. So if we have a confocal system, then also in the Z is exponential, or is Gaussian. But if you have a 2-photon system illumination, that is a polynomial, so it's divided by a polynomial, so that decreases much less as a function of Z that decrease in the other way. So, and that comes from the fact that the intensity along the Z is squared because of we have 2-photon excitation. So all the autocorrelation function, well, not all, as I will show in the application later on today, it starts from a value that actually, this is a log scale, and the value is not defined because you will have to go to 0, and 0 does not exist in there. So we say that this is the limiting value, we call G0 the limiting value of the fluctuation. And what happens is that the limiting value of the amplitude of the fluctuation is proportional to 1 over n, where n is the number of particles. And this is, of course, very interesting point. Okay. Then has a value, since it goes from high to low, where it crosses the 1/2, and this is called the correlation, the characteristic correlation time of the fluctuation, and then it has to go to 0. If it doesn't go to 0, that means that we never reach equilibrium, which is also a very important thing. So this is the correlation function. And the correlation function, how come that the correlation function gives information about the number of particles? So let us make the reasoning in terms of molecules that we have in a volume. So suppose we have 2 molecules in the volume of excitation, and one goes in, so the change will be 50% because the intensity will stay at 1, whatever, and 1 was lost. Okay, fine. Suppose we have 4 and 1 leaves the excitation volume. Well, the intensity total at time t equal to 0 will change by 25% and so on. So you can see if we have 100 and 1 leaves, it will be 1 per 100. If we have 1,000 and 1 moves out or in, we will get the fluctuation, which is 1 per 1,000. So that means that the G0 give us directly the information about the number of particles. And this is very important because we can place our observation volume in the nucleus or in the mitochondria or any other place in the cell, and everyone in the world should obtain for the same system the same number of particles. And so this is a way to measure number of particles, not necessarily concentration, but is universal and is applied, and is a consequence of the fluctuation. So that demonstration can also be done mathematically, where if we know that the average is equal to the variance, I will not go through that because it's in the notes here, and you can show that the G0, so this value of the G0 is proportional to 1 over n average. So this is what we want to say. Well, this is not exactly correct because the volume of excitation, as I show here, is not sharp. So you can see that the volume of excitation is a Gaussian distribution. So a point at the center will have more intensity than the point at the periphery of the point of excitation. And that gives rise to a factor we have to take into account, which depends where the particle is in the volume of excitation. And that factor we call gamma, which simply depends how steep is the volume of excitation. So in general, we have the following expression, which under the diffusion, takes this expression. So if we have diffusion, this is the 2-photon equation, we'll have an 8 here, is always proportional to the inverse of the number of molecules through the gamma factor. And then for each dimension, we'll have a terms of, which is due to diffusion, which is 2 minus 1. So for example, for a 3-dimension, we have -1 and then -1/2. So that will give and this comes directly from the Gaussian thing. And so this is a very general solution. The other thing I want to show you here, that what happens if you have different processes. And this is very important, for example, because today we use molecules that strongly blinking and also are diffusing, and how we can separate the 2 events. Well, there is a general theorem that says that the correlation function is the product of single correlation function for the different process if the processes are independent. For example, if the molecule blinks and diffuse at the same time, but the diffusion is independent of the fact that the molecule is blinking or not, and the molecule keeps diffusing if it's giving light or not, then we can split the total correlation function in the product of 2. And then we can add 3 or 4, 5, 6, whatever processes. And fortunately, in the programs we have today, you choose to associate to the analysis what are the processes that you want to have. And from the point of view of the computer, it's very, very easy because you have diffusion, you have blinking, or any other thing. And for example, here we have the blinking terms, which is used today under some assumption. Okay. So now, clearly, blinking or binding are similar effects. In fact, I call blinking and binding here with the same name. Now, how different is a correlation function if you have diffusion and or you have this binding only term, which is an exponential as a function of time? Well, you say diffusion is a polynomial and here is exponential. It's supposed to be very different. Well, no, it is different, but not enormously different. So for example, suppose the red are your experimental data and you have pure diffusion. So that will be the fit of the diffusion, which will be something like that here. And then you have an exponential term. Well, it will be that one. Yes, it is different, of course. But that difference, if you have noise in the measurement, will be very difficult to study. And so we need different methods we will discuss later. Okay, so first of all, how different are the correlation function? So if you have a molecule, a small molecule which is diffusing water, for example, with a diffusion coefficient of 300 micrometers square per second, you will get something like that. So if you have a molecule with the size of GFP, which diffuse freely in solution, you have 90. So that is a very large difference and you will be able to make. But if you have a dimer of, so a two protein in such a way that you have a dimer, the difference is very, very small. So it will be very difficult to distinguish that. And this is due to the fact that the diffusion of molecule, according to the Stokes-Einstein equation, depends, of course, on temperature, on the inverse of the viscosity, but it depends on the radius of the molecule. And the radius of the molecule depends, well, the volume of a dimer will be twice the volume of a monomer, but that depends on the cube of the radius. So the difference between a monomer and a dimer would be 2 to 1/3, which is a very small difference, which is exactly the difference I showed here. Okay, so let us have some data in order to see how things are and what other points we want to mention in this introductory lecture. So those are HeLa cells, which are expressing a protein, which is adenylyl kinase EGFP in a construct with GFP. And you see those are two cells, and we have a mutant of a, well, it's not a mutant, another form of a adenylyl kinase, which is called adenylyl kinase 1 beta, which has a signal to bind to a membrane of the cell. And then you can see that very well how it binds to the membrane of the cell. So let us follow this table because this table is very important to understand many of the things. So from the point of view of molecules, EGFP in solution will have an average time, will transit time on the order between 10 to the minus 4 and 10 to the minus 3 seconds. But if the same molecule is in the cell, so EGFP is in the cell, it changes by a huge amount. But this is also monomeric, and this is monomeric, and it changes by a huge amount. And then you can add mass by a difference. So the question is, why a molecule in solution will move much faster than the molecule in a cell? And people say, well, it's due to the fact that the cell have viscosity. Well, that contradicts the principle that we and other people have measured, that if you measure the rotational rate of a molecule, in solution or in a cell is about the same. So how can be that the diffusion, translational diffusion, is so different than the rotational diffusion? So the rotational diffusion is the same, but the translation is very different. So something has to be very wrong about what I say. And what is wrong is essentially that I assume that the cell is a uniform space, where there are no barriers, or there are no obstacle to motion, and then translation and rotation, I assume every change in the translation to the so-called general viscosity of the cell. And that was a concept that was, for a long time, everybody was using this concept, but clearly there is something completely wrong about this concept. And if we have time, we will discuss what is wrong, and so how come that the diffusion is so different than the translation. So at this point, I will go rapidly through other observation, that if you measure, for example, this is the membrane of the cell, and you measure the diffusion here, and then you measure the diffusion in different parts of the cell, you will measure very different diffusion coefficient. So here will be, well, here is twice, because there are two values, one for motion in the membrane and motion in the volume observed in the cell. But you can see that those values change by more than a factor of 2. And there is not error in the measurement. They really change more than a factor of 2. And the reason is because the cell is very different. The motion of the same molecule in different parts of the cell is very different. So now we end up with a way to spatially resolve the motion that we need in order to spatially resolve the motion of the cell in order to have information about what is happening in the cell interior. Before I stop this part, I will talk very, very briefly about two-channel detection of cross-correlation. So for example, if you have a given molecule in a given volume and just use this beam splitter, so you still observe the same molecule, but in two detectors separately, all the fluctuations of the molecules will be independent of the fluctuation that are due to the detector. So, hello? Okay, so in the detector side, you will observe some motion due to the molecule, detector 1 and detector 2. But you do the cross correlation, you decrease effects which are due to the detector itself. And this is what was called the after pulsing, and Lionel briefly said that they have detectors that have no after pulsing. So how you treat the cross correlation? Well, the cross correlation, you simply cross correlate the fluctuation in one channel with the fluctuation in the other. And you call cross correlation the cross product of the various things. And so the equations are identical, the same, but you are able to separate colors. For example, if instead of using a beam splitter, you use a color filter that separates, for example, the red molecules from the green molecules. And then you can only observe the one that are common, which will be the one that have two colors. So green and red and green and red. And in that way, it's possible to increase the sensitivity of the method only to the system that carries both colors at the same time. That can be done much better using other techniques that were worked out in my lab by Don Lamb when Don Lamb was working in my lab. Using simultaneous excitation is not only excite everything, but also excite only the groups which are of the molecule which have two colors, and that improves the signal to noise ratio. So I want to go to the end of this part, which is a very important concept, which has to do with what you observe in the cross correlation. And I have this slide because some of the software sold by commercial software make an error in interpreting what happens in the cross correlation. And the error is based on the fact that they say, well, the cross correlation measure only the molecules which are two colors. So therefore, you can measure the concentration of those molecules. Well, this is wrong, and this is wrong for the following reason. So this is a simulation, but pay attention to the value. So suppose in channel 1, which is green, for example, I observe whatever, 100 molecules, which are only green, so they are not in channel 2. And then in channel 2, I observe 50, but the molecules which are together are observed with, for example, 20 in this channel and 20 in the other. So what I measure the following thing. So if I measure the cross correlation in channel 1, I will have 120 molecules, 100 here and 20 there. The correlation in channel 2 will be 50, so it's total 70. So that will be the channel 1 way, and that will be the channel 2 because we observe less. The cross correlation can never be larger than the autocorrelation. Okay, no matter how many molecules you have, cannot be larger. So always will be lower, and the cross correlation will be the fraction of molecules respect to the channel red or to the channel green. So this is what you mentioned. You have to be very careful because I said there is software sold by companies, whatever, that they say that this is a concentration. Well, this is not a concentration. This is the fraction of molecule to respect to the total you have in a channel. So this is important, and it's something that can be done by everyone and figure it out what it is. So I will end up with some questions which might be can give rise to the beginning of a discussion. And I discussed the PSF, and I show the point spread function, and I discussed that the volume of illumination makes the diffusion coefficient to change because it affects the diffusion coefficient. Then I discussed only model for diffusion and not, for example, model for anomalous diffusion, which we can say where it will come from. We see that we can see binding under some particular condition. What happens if we have FET? So this is a question maybe somebody will have. And what happens if we have bleaching in the sample? Those are the most common questions I have when I finish this lecture of the general ideas about FCS. Before I conclude, I want to stress that I focus on single molecule, on the idea that FCS gives us a chance to observe single molecule. And we will see in the rest of the talk I will give, I will always use this concept that we are observing single molecule, and we are observing the properties of single molecule. Can be one color, can be another, can be moving in a very complicated geometry, in channels, in the presence of membrane, and other things like that. And this is still a problem that since the boundaries for motion of molecules in a cell are very complicated, maybe we will never finish to solve it. But we have to be aware that the motion depends on the geometry of the surrounding space. So I will stop here and I will open the floor for discussion. Well, thank you very much.
Thank you very much, Enrico. Wonderful talk. Now we have time for questions.
Well, I already put 5 on the screen.
Yeah. You did the job.
Okay, so let us see.
Let's see if there are some questions from the audience.
You can ask a question in English or in Spanish, whatever.
As I said before, don't be afraid to ask the question in Spanish, and we will translate.
Well, you don't need to translate for me. Well, translate for the other people.
Exactly, for the rest of the people. Yeah.
I have a question. Can Enrico put his video on so people can see him?
Okay.
I do exist.
We don't know that.
Oh, well.
I have to say, is it really Enrico?
So let us see if I can do that.
Maybe Lionel has blocked you.
So the host asks you to start the video. Start my video.
Can you start the video?
It is Enrico. Okay, great.
Oh, you thought that talk was given by the...
I don't know. Maybe it was your granddaughter or something. I don't know.
Oh, yes, they know enough about fluctuation.
Probably.
Okay.
Sorry, I didn't know that my screen was off.
No, it's okay. It's okay. I think it was related also with the configuration that we set up in order to have.
Yeah, because at the beginning I tried to turn it on my video, but didn't turn it on.
Yeah. It was just to have some protection in with the connection and everything.
So you want to protect from my young kids?
So, well, I cannot see further question. Oh, here, Ernesto is raising the hand. So, Ernesto.
Okay. So what is the question?
Muted.
Now we are unmuting him or allowing him to unmute. Yeah.
Ernesto, I cannot hear you.
I trying to unmute. Okay, now I'm muting.
Now we can hear you.
¿Puedo hacerlo en español?
Cualquier
O lo hago
cosa.
en inglés, es lo mismo.
Sí.
No sé quién está. Bueno, lo hago en español y en inglés. No sé.
Casi todos hablan español.
Por eso, por la gente que no habla inglés, por David. So
Okay.
I will do it in English, just in case.
Okay, está bien.
So just two technical questions. I'm not an expert at all. So you mentioned the gamma factor, or the gamma you use to correct, the sharpness of the observation volume.
Yes.
How do you quantify this sharpness? Is it a theoretical one, or you measure like?
Well, it could be a theoretical one if you know the point spread function. So you can measure the point spread function in principle. So you can have a fixed particle, small particle, and scan it, and then you will measure the point spread function. The computer will, given the image, will calculate the sharpness, and then will calculate the gamma factor. However, as you will see in the next lecture, we try to avoid this effect, and avoiding this effect by using different techniques. Instead of measuring the time it takes a molecule to cross the excitation volume, which depends on the form of the excitation volume, we will measure the time it takes a molecule to go from one excitation volume to another excitation volume. And that time is much less dependent on the shape of the point spread function.
Okay. Thanks a lot. And my second question is related to more or less the last part, measuring the diffusion of GFP in solution and inside cells.
Yeah.
And then probably because of the further discussion, what are the models for diffusion inside cells? How do you, so you measure the diffusion of GFP in the cytosol, let's say, and you have not only the differences in volume within the cell, but also, all the mesh of the cytoskeleton.
But the cytoskeleton will be very, very little, because the cytoskeleton is due to fibers. So in 3 dimensions, they affect very little.
Well, yeah, but so accordingly, what we are measuring with Luis Bagatoli, the cytoskeleton, okay, I mean, as a geometrical fiber or rail, we'll say, is very little, but it can perturb or absorb or coordinate, the activity of water.
Yeah, that's a totally different thing. The bound water is a totally different thing.
So my question is whether it's possible, or you have performed some measurements, like treating the cells with nocodazole or Taxol, and having a look to the changes of diffusion.
Well, so
GFP.
First of all, you can measure diffusion using a different technology, which is line scan. So instead of measuring a single point, you can measure a line.
Yeah.
And the line can be sample each point of the line with microseconds, or even shorter than the microsecond. So you can measure in a microsecond, you will see a very, 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 very small volume. Okay, because it will be a motion during a microsecond. So by changing the timeline, the time you take a line, you can change the volume you observe. So you can scan the volume by converting volume in time. By using this method, then you will see that if you go to very small volume, actually the GFP will diffuse in that volume like it diffuses in solution. So it's a question of how big is the volume and how much you average the volume. So if you don't average the volume, you measure very, very small volume, you measure exactly the same value. which is what anisotropy or polarization will give you.
Yeah.
So the point is that it's only the way to measure. If you measure a large volume, you average many different structures. And then, of course, it's not right. Well,
yeah, that's right.
You have an apparent diffusion, which is in apparent in a volume that has many structures. So that's the way to resolve the problem. So going very fast. You can go very fast by line scanning or using what Lionel says, a nano camera. In the AV detector, you have a nano camera, which is only 32 channels, but you can read at about a million frames per second. And that gives you a totally different information.
Yeah, that was my further question. That there are another people asking, but for Lionel or for you, can you, because I haven't seen many FCS measurement with CCD cameras or
yes, actually you can do, because you can measure, as I will discuss, the time it takes a molecule to go from one volume to another volume.
Yeah.
And that requires a thinking about how you can measure the same molecule going from one volume to another, because they have to be the same.
Yeah.
Okay, yes, that can be done. And I will talk this afternoon a little bit about that.
Great. Thanks a lot.
Thank you.
There are other questions.
Before to give the word to Benjamin, I will ask a question here in the chat from Mariana Sartorio that say, which are the advantages of employing FCS over the FRAP?
Okay, so, well, I will answer in English. Is that okay, Rosaria? Well, so the advantage is the following. When you do a FRAP and the molecule replenish the volume, because this is a recovery after photobleaching, you don't know where the molecule is coming from. Okay, so you don't know. In FCS, you can tell where the molecule is coming from. So you lose in the FRAP, you remain to the concept of concentration, and you lose the information about the molecule. And I said before starting my presentation is that I want to emphasize the molecules, not the concentration of molecules. And so the major difference is that you can measure how a molecule replenish the volume as opposed to how the average concentration in that volume change. So FRAP is very different than FCS. Is that okay for answer?
Yeah, I think so.
Okay.
Thanks, Hishisei. Okay. Let's give the word to Benjamin so he can ask his question.
I cannot hear.
Okay. No, now I'm muted. Well, thanks for your lecture, also for David and Lionel. My question is, assuming that the media is not homogeneous, that the probe can partition in two media, and that there are one of those media are small domains that can there are small domains smaller than the point of analysis. Yeah. Is it possible to differentiate between two diffusion coefficients, and assuming that there is no solvatochromic effects also?
Well, the solvatochromic effect is a totally different origin. You are talking about diffusion.
Yes. I want to say that to get the independent of the solvatochromic effects. Yes.
Yeah. So the diffusion of the molecule can be measured by a methodology which is called IMSD, which is image mean square displacement, and you can see volume as small as whatever is fast, whatever is the scanning speed. So the volume depends on how you scan the system.
Yes, but I'm interested on studying domains that are under the optical resolution.
Yeah, for example, basic or things like that. Okay.
So
Enrico, can you show your slide that you skipped over with the beta adenylate kinase that shows both FCS with both diffusion rates in it? You had that nice autocorrelation curve.
Okay, let me see, because I have to.
But I think that would go to the question.
Yes,
I think
Just back up.
to obtain an autocorrelation function that is composed of two diffusion coefficients.
Yeah, this is generally is not a problem. For example, slow and fast.
Yes.
Yeah.
Oh, I see. You don't have the screen sharing.
No, I don't have the screen sharing anymore. But we can have this discussion, Benjamin. We can have this discussion we have time to have this discussion. But
okay.
So you can measure in the same volume, because Dave is right. So in the membrane, for example, you cannot focus in a membrane because the membrane is 5 nanometer, whatever. So you focus in the membrane and surrounding. And so you can still measure, in that case, 2 different diffusion coefficients. I have in the slide, actually, I showed that slide. I didn't discuss how that comes from. Maybe I can re-put the slide if Dave. So let me see.
We can discuss this later.
It's late. Yes. Okay. I cannot find maybe that is the presentation. Okay. Let us see if I can share the presentation and okay, try to go up. Okay, so if I go up a little bit more, I think. Well, it's here. It's some place here. Okay, here is
right after that.
Okay.
Next one.
Okay. So this is the correlation function if you have 2, so one fast process and one slow process, you see?
Yes.
Okay, so this is in the same point, but there are 2 correlation functions. Well, it's not 2, there are only one correlation function, but it's due to 2 processes.
Yes.
Okay. And now here it is the fact. So for example, if you point to this particular point, but remember that the point spread function is much larger than the membrane.
Yes.
So you will see molecules diffusing at about 10 micrometers squared per second, and other measuring 0.1, which are the molecules moving in the membrane. Okay, so you have to be very careful about that, because if you have, for example, a volume which includes a membrane, a molecule will take longer time to get out of the observation volume. Do you see that?
Yes.
Okay, because you are close to a wall. So a molecules can hit a wall and bounce back, but then it will take much longer time. So it will appear to have a different diffusion coefficient, but that you can measure 2 or more process or a distribution of process if you want, like in anomalous diffusion. Yes, you can do that.
I see. So in this case, the diffusion coefficients are 2 orders of magnitudes different.
Yeah.
Is that like the minimum difference in order to be able to observe it in an autocorrelation function?
Well, no. So suppose you have anomalous diffusion. In anomalous diffusion, you have a distribution of a diffusion coefficient. So you can measure the center of the distribution, the width of the distribution, and so on. So you are not limited by separating 2 diffusion times. You can also have a curve which apparently is continuous, but you can fit with a model which is a distribution.
Okay.
You follow what I say?
I see. Yes.
So
yeah. Well, if you don't, in the software will allow you to fit an anomalous diffusion. An anomalous diffusion gives you a parameter other than the number of molecules, gives you a parameter because you assume that the distribution is whatever correspond to the distribution of rates. and then you get an anomalous parameter, which will be 1 if the diffusion is in 1 dimension, and will be 0 if it's whatever, a very, very flat distribution.
I see. Thanks.
That is related to the other issue, which is I have in my question, what happens if you have bleaching? Because bleaching means that you never reach an equilibrium. Okay, and if you never reach an equilibrium, then you cannot do it.
Yes.
Well, you cannot use the same equation. No, it's not true that you cannot do it. You can do very well, but you cannot start with the same equation that everybody uses, because simply you cannot integrate over an infinite amount of time, simply because you never reach equilibrium.
Yes.
And then there is another technique that simply take into account, use the same equation, but integrate with a limit which is given by a given amount of time, which is the time you do the measurement.
I see.
Well, I did only the very, very elementary kind of things. There is much more complicated thing.
Rico,
Yes.
If you agree, and Benjamin, if you agree,
Yes.
move on to the breakout room. So for those of you who ask questions in the chat with Enrico, you will have the chance to discuss with him.
So at what time do we start?
We can back 1:30, and we will have only half an hour. It doesn't mean that you need to stay for the half an hour, the break room.
Well, so 1:30, so will be 8:30 my time.
Yep.
Okay.
So for 1:30 for the next session, okay?
Start, but the breakout room, when is now? I can say it's 8 o'clock here. It's not lunchtime in my place.
They organize the people who want to move to your break room. Dave and me, we are free because we don't have people for our breakout rooms.
So it will appear in my screen.
And you say just showing. That's it.
Okay. So anyway, I will stay here in front of the system. I am here, and now you can see me.
For the rest of the people, we can stay in the general Zoom, or you can disconnect and connect back. I will suggest 5 minutes, 10 minutes ahead of the.
Well, you have to create chat rooms.
Yeah, we are doing this. Don't worry.
Okay. Anyway, I will join whatever. I will take a physiological break. Okay. But I will be back.